Дорогие друзья, начинается секция, очень веселая. Пленарное заседание, не секция, да. Вот, веселая, потому что у нас будет один доклад очный, физический, еще 3 из интернета с самых разных частей света, надо сказать. Просто по земному шару случайным образом раскиданы докладчики. Вот. Ну и первый докладчик у нас Дмитрий Шабанов.
Recording in progress.
Recording in progress. Yeah. Thank you very much, пожалуйста, please. МФТИ, Москва. Об алгоритмических границах для свойств раскрасок случайных гиперграфов. Это тоже тебе.
Да, спасибо за представление. Значит, сегодня, собственно, слайд, название написано об алгоритмических границах, но я буду говорить не только об алгоритмических границах, а просто о границах раскрашиваемости, потому что логичнее начать с того, чтобы отыскать порог, начиная с которого у вас есть что-то, а потом уже пытаться это что-то искать алгоритмами. В качестве мотивировки рассмотрения подобных задач давайте рассмотрим некоторые хорошо известные достаточно примеры из теории графов. Хорошо известно, что ряд проблем в теории графов являются трудно вычислимыми с алгоритмической точки зрения. Например, проблема гамильтоновости графов. То есть мы хотим определить, есть ли в графе гамильтонов цикл или нет, и это полная задача. Поэтому с алгоритмической точки зрения мы ничего не надеемся, кроме вдруг окажется, что P равно NP. Но, в общем, это уже какая-то отдельная дискуссия. Если нужно, там Даниил Мусатову планируется доклад на эту тему.
Сейчас параллельно.
В общем, надо идти туда тогда, если вам это интересно.
В 3 он начинает.
Да, чуть позже. Хорошо, давайте предположим, что мы теперь разрешим себе немного ошибаться. Будем говорить, что у нас есть какой-то алгоритм, который выдает, что есть гамильтонов цикл или нет, но при этом он может немножко ошибаться, с некоторой вероятностью ошибки. То есть рассмотрим, погрузим всю эту проблему в так называемый случайный сеттинг. В случае графов, то есть, грубо говоря, рассмотрим случайный граф и на нем будем пытаться решать эту проблему. Но оказывается, что ситуация резко меняется и все становится сильно проще. Давайте сформулируем несколько результатов на эту тему. Рассмотрим равномерную модель случайного графа. Я обозначил на слайде Geithman. Эта модель устроена очень просто. У нас есть n вершин, и мы просто равновероятно вынимаем из мешка каждый граф, имеющий ровный m ребер. Их какое-то количество, мы выбираем один из них. Хорошо, что у нас окажется? Тогда есть такой старый результат, доказанный в свое время Алексеем Дмитриевичем Коршуновым, что предел гамильтоновости случайного графа, предел вероятности гамильтоновости случайного графа Geithman это будет 0, если параметр n будет меньше, чем 1 минус эпсилон n логарифм n пополам. И это будет единица, если n больше, чем 1 плюс эпсилон на n логарифм n пополам, где эпсилон некоторое фиксированное, но сколь угодно маленькое число. То есть мы его заранее зафиксировали, дальше загнали это в предел по n. То есть, грубо говоря, почти все графы устроены довольно просто. Если у вас мало ребер, то вы говорите, что нет у меня гамильтонового цикла. И вероятность ошибиться маленькая. Если у вас ребер много, то вы говорите, да, гамильтонов цикл есть. И вы тоже промахнетесь с очень маленькой вероятностью. То есть в случайном сеттинге ответ вопрос о разрешимости гамильтонного цикла очень просто. Говорите, смотрим на число ребер, если он больше, чем эта граница n логарифм n пополам, мы говорим да, если меньше, то нет. Собственно, и все. Даже никакой хитрый алгоритм, ничего придумать не надо. Если близко, то это уже, тут может не повезти. Что-то там происходит внутри, потому что там может оказаться, что с положительной вероятностью он есть, с положительной вероятностью его нет. Это уже выглядит не очень здорово.
Если близко, то тоже редкое количество ребер.
Конечно, это шансов, что вы ровно прям поганый граф подберете, тоже шансы ваши ничтожны. Хорошо. Это не да. Теперь зададимся еще дополнительным вопросом. Хорошо, мы знаем, что гамильтонов цикл есть в этом графе, а предположим, мы хотим его найти. Можем ли мы его найти? Хорошо, мы знаем, что он там есть, но ну что, мы опять перебирать все будем? Оказывается, нет. В случайном графе вы можете предложить хороший алгоритм, который будет достаточно быстро вам находить ваш гамильтонов цикл, но при условии, что вы находитесь в ситуации, когда мы находимся вот выше того порога, когда выше порога, дающего нам предельную вероятность единицы наличия гамильтонного цикла. Ну вот есть результат Бола-Баша, уже тоже достаточно старый, 87 года, который утверждает, что есть некоторый алгоритм, я его не стал тут описывать, который при условии, что m снова больше, чем 1 плюс эпсилон n, логарифм n пополам, с большой вероятностью, стремящейся к единице, находит нам гамильтонов цикл в случайном графе. При этом время его работы среднее будет большим от n в степени 4 плюс дельта, где дельта произвольное число. То есть для любого дельта он заработает меньше, чем n в степени 4 дельта с некоторой константой. Ну, то есть там, грубо говоря, n в степени 4 там, и еще что-то малое. Вот. Вот такой замечательный результат. То есть мы даже за полиномиальное время можем искать эти самые гамильтоновые циклы. То есть вообще каждая проблема у нас тут становится никаких нет. Более того, n в степени 4 это, конечно, такая оценка хорошая, полиномиальная, но она все-таки для больших n не очень. Можем ли мы сделать что-то лучше? Оказывается, да, можем. Вот достаточно светлый результат. Алон, но это не тот алон, который...
Да, алон, а рука алон.
Да, это не тот алон, да. И Кривилевич, они доказали, что есть некий другой алгоритм, который, правда, работает не начиная с n логарифм n пополам, а с n в степени 3 вторых, ну, с какой-то константой 35 вот у них получилось. Что он тоже находит наш гамильтонов цикл с вероятностью стремящейся к единице, и при этом среднее время работы, ну вот оно примерно n в кубе делить на 2m. И в общем, на самом деле, несложно понять, что это почти оптимальное время с точностью до мультипликативной константы. Вот, потому что для нахождения гамильтонного цикла нам, грубо говоря, надо обнаружить n ребер, а вероятность того, что там конкретное ребро будет, просто конкретная пара вершин будет ребром нашего графа, это как раз m делить на n квадрат. То есть вот при m порядка n квадрат мы получаем здесь линейное время. То есть за линейное время мы можем находить гамильтонов цикл. В среднем, конечно, правда, тут некоторая такая засада есть, потому что с некоторой очень маленькой вероятностью алгоритм будет устроен так, что надо будет перебрать все подряд. Но вероятность этого ничтожна, и в среднем все хорошо. Вот. Ну вот такой замечательный результат. То есть, когда мы решаем какие-то сложные задачи алгоритмические, в случайном сеттинге эти задачи могут иметь очень хорошее решение, вплоть до линейных алгоритмов. Вот. Но с гамильтоновым циклом все просто, потому что вот у Бола-Баша получилось дожать границу, начиная с которой мы можем гарантировать наличие алгоритма, до границы, начиная с которой мы можем гарантировать наличие самого гамильтонного цикла. То есть ниже этой границы мы просто говорим, что его там нет и никакой алгоритм запускать не будем. Теперь давайте посмотрим некоторые обобщения, некоторый другой сюжет, подводящий нас к раскраскам гиперграфов, и, собственно, в каком смысле мотивирующий их рассмотрение, это случайные булевые функции. Тоже старый классический вопрос. Значит, что мы тут пытаемся делать? Ну, задаваться теми же вопросами, да, вопросы про выполнимость этих самых случайных булевых функций. Значит, у нас есть некоторый параметр k, он должен быть хотя бы 3. Значит, n у нас какое-то большое число, большее k, и мы рассматриваем набор булевых переменных x1, xn, и из них составляем некоторую случайную булевую функцию. Значит, функция эта имеет специальный вид. Значит, вот она записана f от n k m, она задается как дизъюнкция, то есть конъюнкция m дизъюнкций. Каждая дизъюнкция состоит из k случайных литералов. Литералы выбираются случайно и равновероятно либо из набора переменных, либо из набора их отрицаний. Да? То есть всего у нас там типа 2n в степени k вариантов выбрать литерал, дизъюнкцию. Вот. Ну и мы из них составляем конъюнкцию, и у нас получается какая-то булевая функция случайная, уже заданная заранее в конъюнктивно-нормальной форме. Ну, я напомню, что такое выполнимость. Значит, мы говорим о том, что булевая функция выполнима, если существует такой набор значений переменных ε1, ε(n), для которого ваша функция становится равной единице. То есть вы можете сказать, что да, это правда в логике. Значит, у нас она задается, соответственно, эта булевая функция сразу. Значит, это просто выполнимость. И мы еще будем использовать такой термин, как not all equal выполнимость. Это значит, что мы хотим сделать то же самое. Мы хотим получить значение единицы на некотором наборе переменных, но при этом, учитывая, что наша функция задана вот в коммутативно нормальной форме, мы хотим сказать, чтобы не было таких дизъюнкций, в которых одни единички. То есть какая-то тривиальность случилась. То есть мы хотим получить такой набор переменных, чтобы в каждой дизъюнкции у нас присутствовали и нули, и единицы. Вот так. То есть все нули это плохо, у нас все обнулилось, а все единицы тоже мы запретили для симметрии. На самом деле задачи становятся немножко разными, и подходы оказываются в том смысле симметрия проще, но ответ почему-то нашелся для ситуации, когда у нас обычная выполнимость булевой функции. Вот. Ну и, собственно, мы хотим задаться вопросом тем же, каков предел вероятности выполнимости случайной булевой функции, в зависимости от числа наших дизъюнкций вот этого параметра m. Ну, вот картина здесь примерно такая же, как была в гамильтоновом цикле, то есть если m большое, то у нас, соответственно, становится все плохо, если m маленькое, то наоборот все хорошо, почти все функции будут выполнимы. Вот, оказывается, есть некоторое пороговое значение, которая играет роль то, что называется точные пороговые функции. Это результат Фридгуда, такой выводящийся из некоторых общих результатов, которые он доказал. Значит, что теорема утверждает, что есть некоторая, для каждого k есть некоторая МК с крышечкой, такое, что для любого положительного дельта предельная вероятность выполнимости случайной булевой функции это единица, если m меньше, чем 1 минус дельта, вот это МК с крышечкой, умноженное на n, и 0, если наоборот m больше, чем 1 плюс дельта на МКТ с крышечкой умножить на n. Ну вот про это МКТ верится, что оно не зависит от n, хотя формально теорема говорит, что оно как-то должно зависеть от n. Но все твердо верят в то, что это неправда. Здесь просто какая-то функция от k, которая играет роль такого критической пропорции числа дизъюнкций, которые мы берем. n умножить на это число, это, соответственно, некоторое критическое значение.
У нас выполнимость тут обычная, без...
Да, тут и выполнимость обычная, да. Но про новую было чуть дальше скажу. Ну, немного, чем еще люди мотивируют рассмотрение всех подобных моделей, это большой интерес здесь возникает в исследованиях по статистической физике. Я, честно говоря, в физике я не понимаю, поэтому если у вас есть вопросы, то это к Андрею Владимировичу Ляпидову.
А где он?
Нет, что-то я его не вижу.
Вот.
Изучая модели спин-глаз, да, спиновое стекло, или как оно там называется правильно по-русски, физики сделали некоторые интуитивные предположения о структуре множества решений, то есть множество тех наборов значений переменных, на которых наша функция равна единице. Вот. И вот из их некоторых эвристических предсказаний следует, что вот эта наша пороговая величина, вот эта МК с крышечкой, должна иметь определенный вид. Это там 2 степени k, логарифм двойки, минус какие-то константы, плюс что-то, стремящееся к нулю с ростом k. Вот. Ну и начиная с конца 90-х годов математики пытались доказать подобные результаты уже, так сказать, честно, математически, а не махать руками и говорить, что да, вот это очевидно из некоторых соображений. Вот, но это такой экскурс в физику небольшой. Что люди знают? Ну вот была такая серия результатов. Почему-то я тут написал M2 с крышечкой единицы. Наверное, все-таки M3 должно быть, что-то я прям засомневался. Потому что что такое две переменные? Это какая-то ерунда. Или нет? Нет, две переменных, да, там получается единица, правильно. Для M3 неизвестно. Значит, хватал read, 92 год, первые результаты. Дальше вот была серия работ с уже таким более продвинутых в получении более точных оценок. Они уже имеют вид 2 в степени k с константой, без каких-то дополнительных множителей, зависящих от k. Ну вот, наверное, здесь толком нечем комментировать. Значит, получается верхняя оценка 2 в степени k логарифм 2 минус константа, но это немножко не та константа, которая... нет, это как раз та константа, которая нужна. Вот, а нижняя оценка было довольно трудно. Вот последний такой результат 20 лет назад примерно от Леоптас Мур и от Леоптас Перес, вот они улучшали оценку, но у них не получалось вычитать константу. Там. Здесь мы проиграли вообще в 2 раза по асимптотике в первой оценке, во второй там вычитается k умножить на логарифм. Вот, но в итоге все-таки это удалось доказать. Это вот результаты Койла по Найоту. Значит, они доказали, что МКТ с крышки действительно имеет тот самый вид, который предсказали физики, что это там 2 в степени k логарифм двойки минус нужные константы, плюс что-то стремящееся к нулю, причем довольно быстро и экспоненциально по k. Так что это то, что нужно. Вот, но формально...
Оценку по Найоту не улучшить ни на йоту.
Да-да-да, вот. Но вообще, вот чисто формально говоря, это не совсем ответ. Потому что мы получили опять какие-то оценки. И не доказано здесь формально, что, например, эта вещь МКТ с крышкой не зависит от n. Она может просто бегать там, для четных n тут, для нечетных n тут, но все это в каком-то очень маленьком промежутке, зависящем от k. Но k у нас как бы фиксировано, а по n у нас асимптотика в исходной задаче. Поэтому мы получили асимптотическое разложение этой функции при больших k, но вот точное значение не было найдено в этой работе. Но оказалось, что его можно в каком-то виде все-таки сформулировать. Это было сделано в работе вот Динг, Слай и Сан. Я написал 2014+, я не знаю, в итоге публиковали их работу или нет, потому что она безумная. Вот. Но результат очень такой магически сложный, и вообще непонятно, как это можно было дойти до этого. Ну, на слайдах сейчас попробуем это описать. Но это уже некоторые все-таки такой прям теория вероятности мощно пойдет. Значит, как они пытаются записать вот этот сам ответ, чему равно МКТ со звездочкой, с крышкой. Значит, они говорят, давайте возьмем какое-нибудь альфа, число произвольное, которое лежит между 2 в степени k логарифм двойка минус 2 и 2 в степени k логарифм двойка. Дальше возьмем такие вот странные случайные величины xi плюс, xi минус. Это независимые одинаково распределенные случайные величины с поссоновским распределением с параметром альфа k пополам. Далее, для всех распределений вероятностных на отрезке 0,1 мы вводим некоторый оператор r, который приводит это множество в себя. Следующим образом, значит, что мы делаем? Мы говорим, давайте возьмем вот это распределение из этого множества, возьмем последовательность независимых случайных величин, там, это ижитое с плюсом, это ижитое с минусом, таких 2 набора, индексированных 2 параметрам ижи, которые имеют это же распределение, независимо с xi плюс и xi минус. И рассмотрим вот такую случайную величину π плюс минус, ну то есть отдельно π плюс и отдельно π минус, но формула вот задается как произведение по всем и до соответствующего xi с плюсом или с минусом, и 1 минус произведение по g от единицы до k минус 1, это ижитое тоже там, либо с плюсом, либо с минусом. Дальше вы говорите о том, что вот наш оператор r действует на μ следующим образом. Это получается какое-то новое распределение, должно быть распределение случайной величины вот 1 минус π минус умножить на π плюс и поделить на сумму минус их произведений. Вот получается какой-то такой оператор. Теперь, что мы делаем? Значит, теперь мы пытаемся такую итеративную процедуру, да, такую неподвижную точку найти у этого оператора, собственный вектор, собственную меру. Значит, берем μ0 это распределение константы 1/2, просто мера сосредоточена в точке 1/2. И дальше мы запускаем процедуру, что μt это у нас оператор r примененный к μt минус 1. И утверждается, что для любого альфа такая последовательность будет иметь слабый предел некоторый, который как-то зависит от альфа. это μ от альфа будет неподвижной точкой для этого оператора. То есть примененная к нему он будет давать саму себя. Дальше, что мы делаем дальше? Теперь мы снова генерируем какую-то функцию φ от альфа, которая уже не случайная. Это математическое ожидание такого вида, где π плюс и π минус точно такие же, как были на предыдущих слайдах. Единственное, мы теперь в качестве это и житые с плюсом, и это житые просто плюс-минусом, мы берем снова независимые случайные величины, но с этим распределением μ от альфа. То есть мы заменили, там было просто какой-то μ, а теперь мы конкретно μ от альфа взяли. Ну, получается какая-то функция φ от альфа, которая равна вот математическому ожиданию такому. Ну, утверждается, что на нужном нам интервале функция φ от альфа корректно определена, строго бывает, имеет единственный нуль, равный альфа кт со звездочкой. Замечательно. Ну вот, альфа кт со звездочкой это ровно то. МКТ с крыши. Вот такое безумное решение. Ну, начиная с некоторого k, правда. Вот, это в предыдущем слайде было. Ой, потом. Это некоторый нуль вот этой функции φ от альфа.
У нее один нуль?
Да, утверждается ровно один, она убывающий, монотонный, у него только один ноль. Так что да, тут прямо доказывается. Но это удивительный, конечно, результат на самом деле. То есть я вот так на него смотрю и удивляюсь, потому что как до этого можно дойти. Но ладно, до этого можно дойти. Почему нельзя до этого дойти в симметричном случае, когда вы рассматриваете not all equal выполнимость? Я не понимаю в принципе. То есть кажется, что это проще должно быть сделать. Но вот такого результата нет. А вот где несимметричная ситуация, когда вы запустили только нули, оказывается, такой подобный результат есть. Но это математика вполне все приведет. Так, ну давайте теперь поговорим про not all equal выполнимость, что мы здесь знаем. Значит, здесь в принципе ситуация похожая, за исключением того, что нет вот такого крутого результата. Значит, снова есть теорема Фридгуда, которая утверждает, что есть какая-то, на этот раз μ с крышечкой k, но с индексом not all equal, некоторое пороговое значение, до которого у нас почти все функции выполнимы, после которого почти все функции невыполнимы. Соответственно, ну, надо, как всегда, умножаем на m. Значит, и, ну, а так все то же самое. Предел вероятности либо единица, если m меньше, чем 1 минус дельта на наш порог, либо 0, если m больше, чем 1 плюс дельта на пороговое значение.
Можно вопрос?
Да.
Получается, та теорема явной конструкции показала, что m с крышкой от k не зависит от m.
Ну, начиная с какого-то k0, да, именно так. Вот. Ну и про m с крышкой k not all equal то же самое. Есть гипотеза, что это все не зависит от n. И задача, собственно, стоит в том, чтобы это оценить. И вот это уже вещь совершенно тесно связана с задачами раскраски гиперграфов. Вот. Но результат здесь очень похож на то, что было для обычной выполнимости. Значит, снова те же самые авторы, Койоган, Панайоту, и они раньше это доказали, но понятно, это все-таки проще должно быть, чем для в симметричном случае. Значит, здесь единственное отличие, наверное, принципиально в том, что вы здесь получаете 2 в степени k минус 1, а не 2 в степени k, то есть это порог в 2 раза меньше. Вот, но снова вычитаются константы, log 2 пополам и 1/4. Ну и аппроксимация такая же экспоненциально близкая по k. Специально маленькая пока. Вот. Ну и по сути, на самом деле, задача про раскраску гиперграфов, ну не совсем прям честно, что это одно и то же, но асимптотически это одно и то же, действительно, как оказывается. Так, ну теперь я двигаюсь, собственно, к раскраскам гиперграфов. Значит, напомню сразу несколько определений, чтобы, если кто-то вообще не знает, что такое гиперграф и как его надо раскрашивать, то вот слайд для этого тоже был сделан. Значит, гиперграф — это такое, естественно, обобщение графа. Значит, у нас есть некоторое множество вершин. Мы рассматриваем наборы подмножеств в качестве его ребер. В графе у вас 2 вершины в каждом ребре. В гиперграфе может быть больше, и он называется k-однородным, если у вас ровно k вершин. Ну вот, булевую функцию можно очень естественно рассматривать. Да? То есть у вас переменные вершины, там дизъюнкции — это ваши ребра, и вот что вы там собрали, то есть у нас вершины не только переменные, еще и их отрицание. То есть то, что вы собрали в дизъюнкцию, это вот получается набор вершин, ребро. Значит, рассказывать мы будем вершины именно, Значит, соответственно, рассказкой мы называем просто отображение из множества вершин в множество цветов. Будет индексироваться числом R. И, соответственно, когда у вас есть раскраска, вы говорите о том, что появляются цветовые классы. Но это просто набор вершин, покрашенные в один цвет. Да, вот формально цвет — это те вершины нашего гиперграфа, которые покрашены в цвет I. Соответственно, у вас получается такое разбиение. Разбиение, раскраска, по сути, одно и то же. Соответственно, какие раскраски можно рассматривать? Ну, в графе обычно рассматривают только то, что называется обычные правильные раскраски, когда у вас просто две вершины, соединенные ребром, не покрашены в один цвет. В гиперграфе все можно действовать, ребро большое, можно по-разному красить. Значит, мы будем раскрашивать полноцветно. Это значит, что мы хотим, чтобы в каждом ребре содержались вершины всех цветов. То есть, если у нас А — это ребро, то оно имеет не пустое пересечение со всеми цветовыми классами. У вас есть вершины, хотя бы одна вершина каждого цвета. Если у нас цветов всего два, то это то же самое, что просто нет одноцветности, потому что единственный плохой вариант — это когда у вас все время один и тот же цвет. И это то же самое, что обычная правильная раскраска гиперграфа, так что тут вот стык на двух цветах идет полноценно. Ну, некоторая мотивировка, почему стоит изучать полноцветные раскраски. Есть ряд комбинаторных задач, откуда они вылезают, вот связанные, например, с предписанными раскрасками полных многодольных графов. Есть какие-то задачи из теории автоматов. Вот. Ну, а так впервые, наверное, эти раскраски появились вот в работе, знаменитой работе Induction, где появилась локальная лемма, и вот они там тоже это раскраски рассматривали. Ну, некоторые примеры. Значит, у нас тут на 3 варианта. Значит, тут такие маленькие гиперграфы по, соответственно, сколько? 5 ребер. Значит, первый раскрашивается в 3 цвета: красный, синий, зеленый. Первый и второй, те, которые повыше примеры, там все полноцветно, то есть в каждом ребре присутствует все цвета. А вот на нижнем гиперграфе, например, вот самое крайнее левое ребро, тут только есть зеленый и красный цвет, соответственно, это не полноцветная раскраска. Случайный сеттинг, да, вот где мы будем работать, искать наши пороговые вероятности для раскрасок и так далее. Значит, будем рассматривать биномиальную модель. Ну, для случайной булевой функции у вас там нет опции модель рассматривать, там просто взяли случайно намек, там вероятность P особо не введешь. Вот. Здесь мы можем рассматривать некоторые варианты. Ну, все результаты, в общем-то, переносятся с одной модели в другую. Вообще в этой науке постоянно идет какой-то свич между моделями, мы переключаем с одной модели в другую, потому что в одной проще доказывать какие-то факты и так далее. Но все они синтетически эквивалентны будут. И мы рассмотрим биномиальную модель, давайте, случайного гиперграфа. У нас есть n вершин, и гиперграф наш будет k-однородный. И у нас третий параметр — это p, это вероятность того, что конкретное k-подмножество включается в качестве ребра, независимо от других. Вот. Тем самым мы просто бросаем, по сути, монетку над каждым k-подмножеством и включаем его в гиперграф в качестве ребра или нет. Соответственно, задача, которую мы первую ставим, это найти пороговую вероятность для свойства полноцветной раскраски цветов у случайного гиперграфа. Значит, мы предполагаем, что k и r у нас фиксированы, p неограниченно растет, то есть n неограниченно растет, а p некоторая функция от n. Ну вот результаты здесь. Здесь было довольно много результатов. Наверное, я часть результатов упущу, потому что это просто для общего знания того, кто эти задачи занимался. Ну вот впервые вопрос был поставлен в начале 90-х Алоном и Спенсером, который, кстати, выступает на этой конференции.
Оба выступают.
Да, оба выступают. А Спенсер даже в этом разделе, по-моему, у нас.
Да, он прямо
ожидается
скоро выступать.
Да. Ну, в общем, им удалось показать, что пороговая вероятность отвечает так называемый разреженный случай, когда у нас среднее число ребер линейно по количеству вершин, а именно p на c из n по k должно иметь вид cn, где c не зависит от n. Ну, оно может зависеть от k. И, соответственно, они доказали некоторые оценки. Значит, если c больше, чем вот 2 в степени k минус 1 логарифм 2 минус лог 2 пополам, плюс какая-то мелочь, то с большой вероятностью наш случайный гиперграф не раскрашивается в два цвета, c слишком большое. А если c меньше, чем 2 в степени k на k квадрат с некоторой константой, то наоборот раскрашивается. Вот они получили некоторый зазор в котором лежит то самое пороговое значение. Дальше вот были результаты от Recursive Properties деталей, которые улучшат нижнюю оценку до 2 в степени k на k. И вот Recursive почти добили нижнюю оценку до верхней, да, вот тут написано минус 1/2, видите, видно красным цветом вычитается. А у Алона Спенсера это минус 1/2 не было, соответственно, вот получился совсем приятный зазор. Дальше были вот результаты Чиркова с Деборова, и они предположили, чему равно точный порог, но он выглядит ровно так же, как для not all equal выполнимости. Вот. Ну и, собственно, этот же результат получается для случайных гиперграфов, для рассказки в два цвета. Вот это те же авторы, кое Оган понает. Значит, порог где-то 2 степени k лог 2 минус константы плюс мало 1 единицы. Что мы делали? Ну, мы пытались просто обобщить это дело на случай большего числа цветов. Потому что два цвета это там метод второго момента работает как-то лайтово в плане того, что у вас нет никакой матрицы, а получается там функция одной переменной, все сильно проще. Для вот, хотя бы 3 цветов уже там идет оптимизация по набору дважных стохастических матриц. И это, в общем, гораздо более трудная задача. Но вот нам удалось получить результаты, которые очень похожи на то, что удалось сделать для 2 цветов вот, предыдущим соавтором. И именно мы получили оценки, которые близки друг к другу, вплоть до некоторых функций, стремящихся к нулю экспоненциально по k. Ну вот первый результат для 3 цветов. Здесь порог будет значение вот этого параметра c примерно 3/2 в степени k на 1/3. Дальше логарифм 3 еще. Ну и минус константа плюс что-то, стремящееся к нулю экспоненциально по k. Вот. Для R цветов ситуация идентична, единственное, там остаточные члены почему-то другого порядка получились. То есть, если поставить R тройку в эти значения, то там получатся какие-то другие величины. Вот, поэтому по каким-то причинам у нас так получилось. Вот, но R мы рассматривали, когда мы рассматриваем полноценный рассказ, у нас число цветов не может превышать параметр k, и мы рассматривали ситуацию, когда R не очень велик, а именно меньше, чем там 1/10 корня из k. Ну, а k достаточно велико. Значит, здесь у нас снова зазор стремится к нулю с ростом k при фиксированном r и стремится экспоненциально быстро. И основной член, вот логарифм r на r на экспоненту r делить на r-1 в степени k. Вот, но это работы, совместные работы с Николаем Крохмалем и Дмитрием Кравцовым, уже несколько лет назад мы это сделали. Значит, ну, про эти замечания я уже сказал, что мы получили достаточно точные оценки. В том смысле точность такая же, как была раньше, то есть экспоненциально близкая по k. Но возникает вопрос про алгоритмическую границу. То есть, грубо говоря, границу раскрашиваем, если мы отыскали. Ну, там в этих формулах, наверное, можно пытаться еще что-то делать, но лично я считаю, что эта задача решена. Вопрос про алгоритмическую границу. Можем мы предъявить некоторую границу, до которой мы не просто гарантируем наличие раскраски, а можем еще предъявить алгоритм, который бы ее находил достаточно быстро. Вот. Оказывается, можно получить некоторую оценку. И вот первый результат подобного рода был получен еще 20 лет назад Аклеоптосом, Кимом, Correlation детали, которые сказали, что если c меньше, чем 2 в степени k на k, то есть мы находимся примерно в k раз меньше берем порог, чем просто порог раскрашиваемости, то да, есть быстрый алгоритм, который находит правильную раскраску гиперграфа в два цвета, случайного гиперграфа. Ну, вот такой замечательный результат. Но возникает вопрос, вот для гамильтонного цикла мы же добили, там получалось прямо совпадение этих границ. Можем ли здесь что-то сделать? Оказывается, ситуация здесь для раскрасок, она сильно хуже. А именно, есть некоторые препятствия для того, чтобы мы могли надеяться на наличие алгоритма. Но вот это препятствие получило название так называемых алгоритмических барьеров. Значит, мораль примерно следующая. Если мы возьмем c чуть побольше, чем это 2 в степени k делить на k, ну там еще добавим алгоритм k, то множество правильных раскрасок, это некоторое случайное множество, резко поменяет свою структуру. Ну вот фундаментальный результат на эту тему — это работа Аклеоптоса и Койогла 2008 года. Значит, что им удалось показать? Им показали, что если c у нас меньше, чем вот 2 в степени k делить на k с константой, то то с большой вероятностью, с вероятностью меньше единицы, асимптотически почти наверное, множество правильных раскрасок случайного гиперграфа в цвета будет, во-первых, связаны, в смысле Хемингового графа, да, то есть мы говорим, что раскраски соединяются ребром, если они отличаются цветом ровно одной вершины. Вот. Если мы возьмем просто ткнем случайную раскраску, случайно покрасим, то добраться до ближайшей правильной раскраски мы сможем за малый темп вершин. То есть нам придется не так много работы проделать, чтобы перекрасить. И можно предъявить быстрый алгоритм, который бы искал нам эту раскраску. А вот если мы перевалим за 2 в степени k логарифм k делить на k, то есть еще чуть пройдем, увеличим наше количество ребер, грубо говоря, то наша структура это может резко меняться. Происходит так называемое конденсирование. Опять это про физику. Вот. Значит, но математически это означает следующее, что наше множество правильных раскрасок распадается на некоторые кластеры. Каждый кластер будет иметь очень маленькую мощность, экспоненциально маленькую по отношению к общему количеству этих раскрасок. Число кластеров будет, естественно, огромное. Отсюда следует, да. И они будут друг от друга далеко. Хеминговое расстояние между ними будет линейным по числу вершин. И если мы попробуем пройти от одного кластера до другого, организуем путь в таком Хеминговом графе, то он обязательно пройдет через некоторую раскраску, у которой будет линейное количество одноцветных ребер. То есть это прям будет такая совсем поганая раскраска, исправить которую нужно очень долго перекрашивать все подряд. Вот, ну вот картинка примерно следующая, значит, до границы у нас тут так связано, все плотненько и все приятно, значит, на концах звездочки это одноцветные раскраски. Если мы перевалили за границу, то у нас все распалось на какие-то мелкие куски, которые далеки друг от друга, которые трудно обнаружить. Вот, в чем препятствие для алгоритма? Да? Ну, трудно надеяться на то, что мы обнаружим какие-то очень маленькие, искать иголку в стоге сена.
Озеро высохло, осталось несколько.
Да-да-да, вот. Да. Вот. И случайность нам не поможет. Ткнем случайно, будем далеко от каждого из них, и это все равно, что изначально красить все подряд.
Что такое темнота?
Темнота, ну это как бы некоторая концентрация этих товарищей правильных раскрасок.
Да, а вот там же несколько степеней цветов. Что это значит?
Что?
Ну, то есть тут...
Ну, это просто такая схема, то есть это ничего не значит.
Типа количество различных цветов.
Ну, можно считать, что вот это правильные раскраски, это там, которые отличаются совсем мало от них, там что-нибудь в таком духе. Вот. Ну, немножко про новые результаты, буквально, тут осталось 5 минут, да. Значит, я скажу, что нам удалось сделать. Ну, нам удалось обобщить ряд результатов на эту тему. Значит, во-первых, удалось предъявить некоторый алгоритм, который бы находил нам полноцветную раскраску, но уже не в 2, а в большее число цветов с большой вероятностью. Ну вот, это будет верно, если наш параметр c будет меньше, чем вот та самая экспонент r на r-1 вкатый, но теперь она делится на k и еще умножается на некоторую очень плохую функцию от r. Вот, но при фиксированном r это все-таки не так плохо. То есть мы получили снова примерно в k раз меньший порог, чем, собственно, сам порог существования раскраски. Вот. Ну а сам алгоритм, он очень простенький. Мы просто нумеруем вершины. Дальше нумерация вершин задает нам лексикографический порядок на ребрах. И мы пытаемся делать очень простую вещь. Вот, предположим, у нас нашлось ребро, которое еще не полностью покрашенное в R цветов. И число неокрашенных вершин у него осталось достаточно маленьким, а именно от там, 2R-1 до 3R-3, да? Вот, ну, предположим, нашлось какое-то такое по списку первое ребро, то мы просто берем R вершин, которые еще не покрашены в этом ребре, и красим каждый из них в цвет там, первый, второй, третий и так далее R. Вот. Если же такого ребра не нашлось, то есть либо они там все хорошие, либо еще много вершин у нас осталось неокрашенных, то мы просто находим первые R вершин по порядку, неокрашенных в нашем гиперграфе, и раскрашиваем их в цвета от 1 до n. То есть на каждом шаге, получается, мы красим по одной вершинке в каждый цвет. Вот. Ну вот такой алгоритм можно доказать, что он приводит к успеху. Тут идея доказательства состоит в том, что мы пытаемся строить и раскраску, и гиперграф случайно параллельно. То есть мы разыгрываем как бы ребро, проверяем, существует оно в нашем гиперграфе на самом деле или нет. Только в ситуации, если вдруг все плохо. То есть мы подозреваем, что оно может окраситься плохо, но то есть нам неокрашенных вершин осталось мало. Вот. Ну и, так, куда-то я... Да, ну и наконец, вот еще один результат, который говорит, что если мы перевалим за эту границу, которая была в предыдущей теореме, ну вот для 3 цветов это было бы 3 вторых в k делить на k, если мы добавим еще логарифм, знаменательный логарифм k, то и не дойдем немножко до границы раскрашиваемости, то, как мы доказали с Даниилом Тяпкиным, множество полноцветных раскрасок ведет себя так же плохо, как множество в 3 цвета, как множество в ситуации 2 цветов. То есть оно начинает дробиться на осколки, все осколки маленькие, далеко друг от друга и так далее. Ну вот на прошлом слайде было формальное определение того, что мы доказали, да, то есть Хэмминговое расстояние большое и так далее.
Так,
вот. Да?
Пару минут.
Ну, последний слайд. Значит, ну а собственно идея доказательства, она очень довольно трудная, оно использует переход к некоторой другой модели случайного гиперграфа, так называемый planted model, взращенная модель. То есть, когда мы пытаемся взять какое-то множество и говорить, что вот это множество хороших раскрасок, и дальше на нем как-то строить гиперграф, то есть не по гиперграфу получить случайное множество, а наоборот пытаться действовать с другой стороны. Вот. И очень важным элементом доказательства явилось утверждение о том, что свойство наличия большого числа полноцветных раскрасок также имеет точный порог. Вот это хорошо известно, что просто наличие полноцветной раскраски имеет точную пороговую вероятность. Но нам надо было доказать, что если у вас свойство раскрасок не одна, а там какая-то экспонента от n, вот, то вот, это тоже имеет точный порог, и для этого пришлось передоказывать в каком-то смысле теорему Хатами-Малоя 2008 года. Вот. Ну, в детали доказательства я, конечно, не влезаю, потому что это слишком сложно. Наверное, все. Всем спасибо.
Друзья, у кого вопросы?
У кого есть вопросы, Федя? Через этот надо тоже через микрофон.
Рассматривалась аналогичная задача для списочных рассказов гиперграфа для пороговой вероятности.
Эстафета.
Ну, вопрос очень трудный, потому что списочные предписанные раскраски, у нас же там нет ограничения на количество цветов, как бы изначального. Из-за этого как бы вся наша история там с вычислением моментов и прочих вещей, естественно, не работает. Да, поэтому это какая-то экстремальная величина. И вот, не знаю, там вообще как бы в ситуации, когда у вас есть разреженный случайный граф или гиперграф, например, с предписанным хроматическим числом, все не здорово. Там про него не так много известно, как про хроматическое число, в принципе. Вот, поэтому да, нет, мы не рассматривали, но это интересно, потому что дальше много трудно.
Не, ну скажем, вот это число, которое там m от n, да, сколько нужно верно, чтобы нельзя было раскрасить,
да.
Списочное исследовало, если она ведет себя похожим образом.
Ну, безусловно, да, но там все-таки экстремальная задача просто на маленьких графах, а здесь у нас огромный граф и все плохо в этом смысле. Потому что мы не можем вычислять моменты и так далее. То есть у нас много этих раскрасок хороших. Мы пытаемся понять его структуру, там, вычислить моменты, так далее, концентрацию. А для списочного хроматического числа непонятно, что сделать. То есть как бы мы не можем взять, вот мы можем конкретный список взять из него что-то посчитать, да?
Сразу непонятно, но
да. Ну нет, я говорю, интересная задача, да, но такие точные результаты точно не видел вообще.
Спасибо. Так, еще есть вопросы?
У меня простой вопрос. Там, почему раскрышка? Да я так. Почему раскрышка 2 равно двойке?
Единица. Единица. Нет, там была точно единица, но если у вас, ну это как в случайном графе, если у вас сумма от n ребер, да, то есть там меньше, чем 1 n, то вы там начинаете раскрашиваться типа в 2 цвета или что-то в этом духе, вот примерно в таком духе. Если больше, чем 1 n, точно нет. Вот как-то так, ну это очень похоже на это.
Ага. So I want to present one of the leading specialists in game theory in the world, Professor Hervé Moulin, and his talk, Ex ante fair division.
So thank you for the invitation. You know, I'm sorry it has to be online, but such is life sometimes. And I want to present here some general topic in a sense about fair division and normative economics in general, which is becoming rather prominent as a source of both natural questions and difficult mathematical problems, which I think is particularly striking there. Okay, so it's about the concept of guarantee. Let me write. The concept of guarantee, which is also the one that you can call ex-ante fairness, hence the title, and it has to do with a view of a fair division problem, which you try to look at ex-ante. What do I mean by ex-ante? I mean before an actual negotiation or mechanism or some interaction as organized by the manager will take place. So the idea is to get something concrete, and I think it will immediately be clear what's going on here. The idea is to offer a worst case evaluation of the particular mechanism to each agent. So for instance, when you look at what's the well-known guarantee and inequality introduced by Steinhaus in his original model of cake division, what is it? I mean, let's see if I have a bit of room for a picture. Yes. So Steinhaus was saying something like this. We have a cake, which is really a measurable subset of some probability space. And over the cake, each one of us has a utility for shares of the cake, which are represented by some measure, some positive additive measure. So my utility for share S is going to be the sum over S of some DUI, some density, for instance, or some probability measure on the cake. Okay, all right. So, so now he was saying something like this. I mean, I'm going to propose to you a mechanism which resembles, in some sense, the divide and choose mechanism. I will come to that later. But I can guarantee to you that no matter what happens and no matter who are the other people partaking in the mechanism, for yourself, the share that I will end up giving you, your SI, will be such that UI of SI will be greater than or equal 1 over n of UI of omega, right? So the guarantee here consists of the following. You tell me your utility. You don't lie, you just tell what's the correct utility, and then you can go home if you want. If you can go home and give me full control about what's going on, and I will act on your behalf as a proxy. And then I cannot tell you exactly how much you will get because it depends on what the others are going to be, what kind of utilities and so forth. But I can guarantee you that in the end, you will get at least this amount, which is really your worst case utility.
This is for
yes.
convex.
Excuse me.
For convex utilities, this makes sense. Yes. Otherwise, you can. Or for concave utilities, the issue of concaveness of convex.
The utility is additive, right?
Yeah.
Is that it's a measure, it's a positive measure, but your share does not have to be a convex.
Utility of pieces, yes? Exactly.
Yes. Your share can be arbitrary, but you can guarantee that. And why can you guarantee that? Well, that's a fairly simple application of the Lyapunov theorem of, about non-atomic measures, vector measures. Nothing really deep, but still a nice remark. But right now, I'm just illustrating the concept, right? You know, this idea, I give you this, this guarantee in advance. And so this is the interpretation here. You can think of it as an ex-ante contract in which there is the mechanism designer and a participant, and you just say, look, I let you do things in my, on my behalf on the condition that you guarantee that much. But there is an alternative interpretation, which is just as good, I mean, just as relevant, which is to say, okay, you don't give that as a you know, a devolution of all the decision power to the manager, but you say, okay, I'll participate in the negotiation. I'll try to have a good, you know, I play it well and so forth. But if I'm not happy with what we come up about with what we end up recommending, I can always invoke my guarantee. So I can say, no, sorry, it didn't, I didn't like what happened. So I want to go to my disagreement point, and in my disagreement point, you have to give me at least 1/10 of the total value of the cake. Okay, so it's the same thing if you want, but one could be played in some sense exposed. Okay, all right. So this theme has been very important in the fair division literature. As I said, it started with the work of mathematicians in the 40s and the 60s and so forth. But then it was also very popular in the context of microeconomic theory and the so-called Arrow-Debreu models of consumptions of commodities, where it's called the equal split lower bound. I mean, we will come to that tiny bit later. And recently, a lot of activity has been devoted to that context, to that problem, sorry, to that notion of guarantee in the context of the allocation of indivisible goods. So instead of having a cake and a non-atomic utility like I had here, it will be exactly the opposite. I mean, you have just a bunch of a finite number of indivisible goods and additive utilities. But I will not really review that literature in detail. I will give you an idea of what it is at the end. Okay, also some similar things in other contexts, with, which I'm, of course, happy to discuss offline. All right, so let's go straight into the model. By the way, I will be grateful for a reminder when I'm left with 5 minutes for talking. Is that, if that's okay?
Yeah, okay, so 5 minutes
no
before.
Yeah, just tell me, 5 minutes before I must shut up. So, all right. Yeah, so, but I'm okay with the questions in the middle, of course. So we have a bunch, yes?
No, I said.
Yeah. We have a bunch of agents, a finite number of agents. And then to define the concept, I remain abstract about the set of feasible allocations. So feasible allocation means that an allocation Z will give some kind of consumption Zi to agent I. That could be a share of the cake, that could be a bundle of some commodities, could be whatever you want. Okay, the important thing here is I will respect symmetry. In other words, this set, the set of allocation must be symmetric in N, because I'm going to have a notion that everyone is entitled to the same level of guarantee, which is, of course, the simplifying assumption, but it's the most, by far, the most important case. So, all right. Examples, so these are examples. You can be a bit more general, but in fact, I will not be more general than that in the talk. It could be that this set is defined by the fact that the sum of the vectors Zi is a certain bundle of commodity. That would be the Arrow-Debreu, the Arrow-Debreu context. But it could be alternatively that these Zi's are this time capital and they are share of a measurable subset. And that is in fact a more general context, because as you can imagine, I mean, you know, there is a potentially a much richer structure. All resources will be distributed, and that's why you have expression like this, symmetry, because they have equal rights. Okay, and then in fact, everything will be about ordinal preferences, but as usual, for convenience, it will be represented by a utility function. Now, the last ingredient in the definition of the concept is the domain of preferences or domain of utilities. I mean, I don't make, and that of course is a critical element for anything in mechanism design or in fair division, of course. Okay, and a notation, this is for a utility profile. It gives me a full utility function, and the utility UI is a utility function over the feasible allocations, and what I call utility profile determines a utility for each participant. Okay, so now here is the key definition. So you are giving me the set N, you are giving me the set of allocations, and a domain of preferences. When I say you give me the set N, I only mean you give me the number N, how many people are involved. Okay, and what we will call a guarantee will be a mapping from any utility in the domain to a number. Okay, now I want to insist on something here. I don't want to fool people by having this little index I here. I keep the little index not because the concept has to do with a particular agent I, but because I want you to keep in mind that this is something about an individual agent. That's the whole point of the concept is that. I mean, it's a single participant who is taking his utility and saying, okay, from this utility, the function gamma will give me an R, which will be, as you will see in a second, a utility level, a minimal guaranteed utility level. So this function gamma has to satisfy a critical property of compatibility, because if you give me a profile where the U1, U2, UN are potentially very different, now each participant can compute his or her guaranteed utility individually without paying attention to or without knowing what are the other utilities. So therefore, this number only depends on UI. Nevertheless, it must be, so everyone does this computation, but now it is possible to find, given any profile, some feasible allocation in which those promises, if you want, are actually implemented. Okay, so you can sense, of course, that since there is this compatibility of meeting at the same time all of these independent demands, this will severely limit what we can offer in terms of the function gamma. All right. Now, two very natural concepts. Once we define the guarantee, is the notion of maximality and then dominance. Maximality means that this function gamma, which satisfies this definition, this feasibility property, cannot be improved. So, of course, if gamma meets this property, anything below gamma will also satisfy the property. And what's interesting from the point of view, in particular, of fair division, is to have a high guarantee, because I am much more willing to participate in a mechanism in which my guarantee is higher. I mean, in the Steinhaus model with the cake division, I could tell you, okay, I give you 1/2n, 1/2 of the guarantee that Steinhaus is actually able to offer you. So you prefer to be safe in that dimension. So you look at maximality, which simply says that the function gamma as a function from the domain into R, a real valued function on the domain, cannot be improved if if you have another, here the notation is that this is the set of guarantees, the set of function gammas. So if you have another guarantee which happens to be everywhere for every utility above gamma star, then they must be equal, so there is no way to improve, okay? And again, also completely standard, there is the dominant guarantee. If it happens that there is a single maximal guarantee, namely one that will in fact be above every other guarantee. So obviously, as I'm sure everyone realizes, the maximality is a weaker property than dominance, and we can certainly have problems in which there are maximal guarantees but no dominant one, as well as we have problems in which there will be dominant guarantees. Okay, so here is the ultimate goal, which is in fact a very difficult goal from the point of view of the mathematical difficulty, is to uncover the full set of maximal guarantees. And of course, in some specific models, specific domains, not too complicated. So this may be a good time to pause for 30 seconds and ask if anything in this abstract requires some clarification.
Микрофоны, да?
Yes.
Yes. Yes.
Yes. So what does this greater or equal mean? Is it in the Pareto sense?
Yes. Which one? Which one?
Where gamma is greater or equal than gamma star.
No, simply a function above the other for each value of UI. I should have said here that the n is fixed. So
and for each
agent, the function
UI.
Yes, gamma of UI is greater than or equal to gamma star of UI for all UI. And of course, as you remember, the I means nothing. I mean, what I mean is that UI is moving in the domain. Yes.
Yeah. So guarantee, you have a fixed environment of the set of divisions, and then you vary utilities, utility profiles. And the guarantee, ex ante, you do not know on which of the divisions the guarantee is realized, so to speak, yes?
You don't know who the other people are. You don't know what their utility is, and you want a guarantee because you are a newcomer to the bargaining, you are risk averse. These people, they may be very good at playing the mechanism and they will screw you left and right, but okay, if I just know my utility and how many people are involved, I know I get that securely. Yes, that's exactly the thing. The whole point is that it does not depend on who the other people are. Yes, absolutely. Okay.
Okay.
Yeah. All right. Okay. So let's do some examples. No, sorry. I have to introduce a critical concept and a very simple fact, which is also completely fundamental, really. Here is the maximean upper bound. I mean, in this very abstract, very general definition, there is already a concept which is compelling, which obviously is going to play a role, and a big one is the notion of max-mean guarantee, or no, I should not say guarantee, max-mean upper bound. What's the max-mean? That's, okay, again, it's something defined for my utility and how many people are playing the game or whatever game with me later. So it's going to be the max over the set of allocations of the minimum of shares that I will experience. So now you see here, I see that I did a typo. I should not have kept this I as the same here and there. I should have said K. Here there is a K, and this is ZK. Why? Because remember, this is a problem in which only agent I is involved. Nobody else is involved. He's saying, okay, there is this cake to divide, And let's suppose I divide it like this because n equals 3. And let's suppose that I think of this partition in S1, S2, S3. Okay. All right. So if this partition is offered in some ways to us, and if I get the worst possible of the 3, this I will get the mean of UI zk. And this is, well, I should have said Z1. This is really Z1, right? This is Z1, this is Z2. Sorry, it's getting a little bit messy. This is Z2, this is Z3. Okay, I think you get the idea. And okay, so you think of yourself here in computing the max min, you think of yourself as acting as the divider in a divide and choose sort of mechanism, right? Let's you split the cake in 3 shares and you say, look, if I get the worst of those 3 shares, how much would that be? So now, because you are in the position to choose this partition, what you can expect, if you know that indeed the final allocation will be like that, what you can expect is at least the minimum of those 3 shares, right? Now, why is that important? Why is that important? Is because you have the sort of the general statement here for any actual feasible guarantee gamma, it must be that this max min is an upper bound. And the argument is extremely simple, but critical, because, okay, so let's assume we have some guarantee and we consider this quantity max min. And now let's think of the profile U star where everybody has my utility. Okay, the unanimous, and this could happen. It could happen that everyone is like me. And if everyone is like me, I know that the profile of utilities gamma of ui n, the same for everybody, gamma of ui n, etc. Gamma of ui n, that profile of utilities is feasible, right? That's the definition, that's applying the definition to this particular profile. But if that profile of utility is feasible, this will be implemented by some shares S1, S2, Sn, and all of these shares must give at least the utility gamma of ui n. So, so therefore, my guarantee must be at most the minimum of my utility for those shares. Do you see the point? You see here, I know there is S1, S2, Sn, that's a feasible partition of the cake, right? Which is such that U1, S1 is bigger than gamma ui, sorry, ui S1 bigger than gamma ui n, and the same for S2 and the same for S3, etc. Right? So you see that, of course, the gamma ui is going to be less than the minimum of all those, right? That's why the gamma is going to be less than the minimum of those terms for some feasible allocation. Therefore, it is less than the maximum of this mean over all potential allocations. Okay, a very simple. Once you think about it for a minute, you know it's rather clear, right? No questions about that one. So because this is really important. I mean, it tells you, okay, if it happens that the max min is actually a guarantee, then of course it's the best one, because that's what we said. You know, what I'm saying here is if max min is actually feasible, it is a guarantee which dominates every other guarantee. That's exactly the definition of dominance, and we are done as far as describing this notion of guarantee. That's it. No need to look further, because nothing else is interesting. And this is the canonical guarantee. And of course, the point will be that in many contexts it works, but in many other contexts, this doesn't work. This is not, okay?
A guarantee at all.
Yeah. Say that again.
Actually, it's not a guarantee at all. Yeah, not a guarantee.
It could be. No, I'm saying in some problem, if you choose the set of allocation and the domain in certain ways, sometimes this is true, and I will show you examples. Okay, but there are also examples where it's not. So let's go immediately to the example, because here I take the model which you could think of in a sense as the simplest, at least from a mathematical point of view, maybe not from a microeconomic point of view, but who cares at this point? We have one unit of a divisible thing to distribute. I say a divisible asset liability because what I have in mind is, for instance, this is what I am distributing are the shares in some venture, in some business ventures. But the business venture can be looking good, looking bad. You actually like very much that business, to be involved in that business. Me, no, because I think it's very risky, etc. So the domain of utilities is anything which is a continuous utility between 0 and 1. Remember, one unit to distribute, so the sum of the ZI is 1, each one gets a non-negative share, and I am allowing any continuous utility, right? Without making any monotonicity assumption. For you, for instance, you can have the utility can really be, by convention, I think I should have put it here. The convention is that UI of 0 equals 0. That's just a normalization. It has no meaning. But then on 0, 1, you can have anything you want. All right. So, yes. No. Okay.
Yeah.
So as it turns out, I mean, this is actually already a very difficult problem to identify all maximal guarantees in that domain. At the end, I will tell you a reward. I offer a reward if someone can help me solve that problem for this particular domain. But let's start. Max mean for this problem is not a guarantee. Why? Just take the case of 2. So a division when you have only 2 agents is going to be I give x to one of them and 1 minus x to the other. And therefore the max mean is max over x mean of uix and ui 1 minus x. And I say that this is clearly not feasible. And I think you will you have understood that already, but let me draw a picture. It's simple. So on 0, 1, let's say that, right. Let's say that, I'm going to use the nice colors. So I have one agent whose utility goes like this, right? With 2 peaks, and the peaks are symmetric. So this is a certain x star, and this is 1 minus x star, right? So therefore, the max mean of this agent is to get the best. And I guess now you see me coming. It's kind of obvious that the other. So that was U1. Now the second agent, he's like this, and with the peak at 1/2, right? Peak at 1/2. So he's also expecting from max mean the maximum, and obviously you cannot give them both their maximum, right? Simple and obvious. Okay. Now another very simple and obvious observation is the following: equal split is a maximal guarantee in that domain. So it's a guarantee. Why? Because it's always possible to give to everybody the level UI of 1/n by just giving 1/n to everybody, right? So no problem, it's a guarantee. Now, for the maximality, I don't do the exercise. I mean, I don't have time, but it's a simple exercise. You can check it. There is no, if you try to define something which is better than 1/n for everybody, you cannot. It's not very difficult. I just don't remember right now exactly how to do it, but trust me, it's not hard. So what I did here in the slides, and I'm running out of time already, so I'm not going to go very over that. You can easily relatively easily compute the set of what are maximal guarantees, and in particular, if there is a dominant guarantee on interesting subsets of quasi-concave or the so-called single-peaked domain, or the domain of single-dipped preference. And the single-peak domain means that the utility on 0,1, for instance, is going to have will be quasi-concave, so that the upper contours will always be convex, and single dip is the opposite, where the utility goes something like this. Okay, so you get some fairly simple expressions. For instance, you see that in the single peak domain, the max mean, the UI 1/n is actually a guarantee. And this has to do with the convexity of the preferences, because the upper contours being convex. So why is that? I will just do this one. Why is it? Okay, so we know that UI 1/n is a guarantee. Therefore, we know that max mean is at least UI of 1/n, which is obvious. And we want to show that max mean cannot be more, right? So what would it mean that max mean is strictly more than this? It would mean that you can divide, you fix a certain utility UI, and you can divide the unit 0,1 into Z1 plus etc. plus Zn equal 1, such that each UI of Zk is strictly greater than UI of 1/n. But that, by convexity of the upper contour, means that this is not possible, because then the 1/n of sigma of UI of Zk would have, wait, sorry, it's not this one, it's the other, it's the UI, it's the UI of, oops, yeah, here I'm talking of the UI of 1/n of the sigma of the Zk would have to be also bigger than UI 1/n by convexity of the set of the upper contours above 1/n. And of course, this should be an equality. Okay, so as long as you have these convex preferences, everything is simple. You get 1/n and you are done. Very good. But then when you have the opposite of convex, where this time it's the lower contour which are convex, you get a different expression. Nothing very complicated and nothing very hard to prove, but okay, it takes a little work. And then I have also here the description. If you are interested, since I will send the slides, where I can explain it, it's a nice exercise. But the very open question is, what about this general domain? What about the general domain, all convex, all continuous functions over 0,1? What is this? What is the? What does it look? a maximal guarantee, I already said that UI of 1 over n is 1. That's fine. It's one maximal guarantee, and I can show you quite a few more. I can show you quite a few more by taking inspiration from the voting model. And I'm just going to do here for 2 agents. I have 2 agents, and what I do is I take an odd number of outcomes, outcomes meaning numbers in 0 and 1, between 0 and 1, and then I give as a guarantee the median of the utility over the sequence of the A, B's, and 1 minus B, 1 minus A. So I should have said here probably that I take Q outcomes A, B, C, etc. Q outcomes, then the outcome 1/2, and then 1 minus A, 1 minus B, ordered like this. Okay, so this is a guarantee. Why? Because when you have only 2 agents dividing one commodity, you can think of that as a voting problem. If you change my utility for 1 minus X into my utility for X, for giving you X, instead of me getting 1 minus X, then we are in fact deciding jointly on what will be your share. And that's enough to determine the final share. So then at that level, if I tell you, okay, there is an odd number like that of an increasing sequence with an odd number, and I allow you to choose to eliminate exactly Q, each one can veto Q out of the 2Q plus 1. Everyone can be, both players can be allowed to do that, and there will still be something feasible remaining. Therefore, if they each veto their Q worst outcome in this list, they will guarantee for themselves the median utility level, and it will be feasible. You see the argument? It's just this idea that you have an odd number of possibilities. Everyone can veto just a little less than half, so that after the veto, even if the veto exhausts the maximal number of options, you will at least have 1 left. And then that shows that by vetoing your Q worst, you end up at least at the median. So what I find an interesting and to me very obscure open question is, okay, this is even in the space where when you have only 2 agents, you are transforming the problem into a discrete problem. Of course, it's very general because you can take any sequence, but what would be a more interesting type of guarantees which use more richly the continuous nature of the model, which uses some density function or something?
5 minutes.
Say that again?
You have some 5 minutes.
Okay. All right, time flies in your company. All right, so simple. Yes.
So that's why.
So so now divisible resource, the general cake division model. So what we know, and that's the Steinhaus model, that's the one I mentioned at the beginning. Everyone has a utility which is non-atomic and additive, and over the cake, right? And in that case, the share, the guaranteed share, I give you 1/n of what the cake is worth, the entire cake is worth for you, is dominant. Okay, maybe I can put a little bit of light here. It's getting dark here in Scotland. Okay, all right. So that's dominant, that's fine. Now, what can we do when we don't have at all this additivity? We don't even have a measure, but we preserve the non-atomicity. So we are dividing things which are non-atomic, so there is no particular point in the set that has any weight. And you can always make compromise by going continuously from one value of utility to another or over two sets. And I still want to find some possible guarantee. Here I skip that one. Okay, so max mean is not a guarantee. That's very easy. For instance, the counter examples I had before will work. But here is a nice, I want to just now show one nice theorem that, that we got recently, a group of people, as you will see. It's instead of the max mean, now we're going to look at the min max. The min max utility instead of max mean. So we're going to reverse the mean and the max. I mean, the usual thing, right? You had max of mean, now you do mean of max. And so the max of mean, when I had the max of mean, max over the allocation of the mean UI of ZK, this was the utility of my worst share over the best possible partition of the cake. And now I'm looking at the utility of my best share in the worst possible partition of the cake. So you see that I'm putting myself, instead of being in the position of the divider, now I put myself in the position of the chooser. Somebody is proposing to me a partition, possibly the worst possible, but at least I'm allowed to choose the best one, okay, my best share. And this gives me the level min-max. In general, I mean, if you don't have, for instance, the non-atomicity condition, it is not true that the min-max is less than the max-min. But here is a theorem which we obtained in two parallel papers, which were at some point a joint paper for MOR and then became two parallel papers again in the same journal. One by the economist with a flavor of mathematics, and two, those are the two people here, and then here two mathematicians, very talented. I don't know if they are part of the audience here or one of them, but if they are, hello. And because this, yes?
Роман Карасев, no?
Роман.
If Roman Karasев is well known here, yes.
Okay,
He's not.
That's okay. So the min-max is actually a feasible guarantee. The min-max is less than the max-min, and this for any non-atomic. Here the utilities are, I did not define precisely what the utilities are, but they are very general in the sense that they are just continuous with respect to a simple topology over the measurable subsets, something like, you know, distance of sets or with respect to some underlying measure in the probability space. So essentially you want the property that if I give a set S and then a bigger set T, and I have my utility going from U of S to U of T to UI of T, I have the continuous value, intermediate value theorem between U of S and U of T. And so you can always move smoothly in terms of utilities from one set to the other. And that is the key property that allows you to show a critical lemma, which is that because of this property of non-atomicity properly expressed in a topological sense, if you give me any utility and any subset of the cake, then there exists an equipartition of the cake. For me, I can split this subcake Zi in shares which are all of equal value. And because of that, when you apply it to the division of the full cake, you can see that if I have a partition in which all the values are the same, and this one I call the total value for the partition, then of course this is going to be less than the maximum of the worst share, because all the shares are the same, they are all the worst share, and the minimum here of the best share, because all the shares are the best, because they are all equal, right? So that's why min-max is less than max-min. And in fact, this partition lemma is the tough one, is the one where Avakumov and Karasev, they use the really advanced tools of algebraic geometry to prove it. And once you have that, the second step is to say, aha, that's good, because now we can adjust the a certain simple, I mean, not simple, but a certain known generalization of the divide and choose method, generalization to more than two people, to implement that lower bound min-max. That is to say, to make sure that everybody will end up at least at the min-max level. So I guess now I have reached my time limit. Am I right, or not quite?
Yeah, more or less, yes.
Right.
And maybe some questions, even we have some time for questions. Yeah.
Yes, yes, sure.
Yeah, first question is of mine. Am I right that results of slide number 7, approximately 7, I don't remember. They use the very rich set of allocations when any allocation with the sum of the type equals to 1 is present.
You are talking, yes. Are you talking the division of one unit of some commodity?
Yeah, exactly,
okay.
Exactly.
Okay.
So any is available.
Right.
If you somehow restrict the set of divisions for some reason, then results became unknown. Yeah.
Then the result become more positive. Yes. You're saying, okay, at first I'm allowing a very general domain, all the continuous functions, and then and there I cannot answer what are the maximal guarantees, but then if I reduce considerably the set of utilities, for instance, single peaked, then it's okay. I mean, then it can be, you can know. Yeah.
Yes, but if you restrict the set of allocations which are available, if there are some results on restricted domains, not domain when you divide one unit in arbitrary way, but in
yes.
some.
Okay, that's a possibility. It is possible that some type of restrictions on the possible divisions would help, but frankly, right now I don't have any intuition for which kind would be useful, because okay, so here now the allocations are simplex, and now you want a subset which has a better structure. Yeah, it's not obvious to me, but it's an interesting idea. Yeah, maybe some restrictions of the allocations themselves, of course. Yes, absolutely, it could.
So, I present Andrei Kubavsky, MIPT, and the CNR. What is CNR? S. CNRS, Paris, да? CNRS. Yeah, okay. So, you are welcome to take a floor.
It's good. The first typo is already on the title page, so this way I'll keep you awake, hopefully. So this is a joint work with Dima Zakharov, who is an extremely talented undergrad that just went to MIT for a PhD, and it's about a new approach to deal with a class of questions in extremal set theory, which I can call forbidden intersections theorems, but not only. It can extend to larger things, larger problems. And this is a method which is which uses random restrictions and the recent breakthrough result of Alweiss, Lovett, Wu and Zhang on the sunflowers and robust sunflowers. So let's begin. I'll try to give some proofs and not to be too hasty. So if you have any questions, please interrupt me and ask. Okay, so what are we working with? We will be working with families of sets. So this would be my standard notation for the set of first n natural numbers, n in square brackets. And if I have a set X, then I'll write 2 to the power X for the power set of X, so all subsets of X, and I'll denote by X choose K, or the set of all K element subsets of X. And any collection of the power set of n, I will call a family. So a family is simply a collection of sets. So as a warm-up, I'll present a classical result by Erdős and Rado on sunflowers. But first, let's see what is a sunflower. A sunflower is a collection of sets, P1 to PT. Here I should write, I guess, a T sunflower. S, P1, etc. PT. If the intersection of any two sets, petals, is the same as the intersection of all petals. So any two different intersect in the same way as everybody. So graphically, you can think about it as follows. Let me do a sunflower. So you have the core, which is the intersection of everybody. And then you have the petals. I mean, the choice for the colors of the sunflower is not very realistic, but something like that. So this is the common intersection, and the the green blobs do not intersect elsewhere, and this would be our P1, P2, etc. PT. It's a very useful object for many in many cases, and they appear throughout combinatorics, but not only. Different topics in computer science, like communication complexity or Boolean circuit complexity, and yeah, somehow it's very useful because it has a very clean structure, and one of the fundamental questions in extremal set theory, one of the main questions, is how big should a family be so that we can guarantee that it contains a sunflower? So here is the first result on this topic, which is by Erdős and Rado. And it says that if we have a collection of sets of size at most k, so the ground set here is not really important. I write it here, but it doesn't really matter. So we have a collection of sets of size at most k, and the family is sufficiently large, so k factorial times t minus 1 to the power k, then it contains a T sunflower. So this is another nice feature of sunflower. So it's a structured object, but it's also somehow an unavoidable object. So these configurations you will see in sufficiently large families. So let's prove this. If the statement is unclear, please ask questions. So the proof is by induction. on K. So for the case K equals 1, it is obvious. Let's see why. Because, well, if you have sets of size, well, you don't have sets of size 0 because then itself it forms a sunflower actually, but well, that doesn't really matter. So you have, let's think about sets of size 1, and then of course all of them are pairwise disjoint, and with set of size 0 as well. Let's put it this way, and all of them are disjoint. So all of them, any subset of them would form a sunflower. And this statement says that basically if you have more than t minus 1 set, so this would be 1, this would be 1. So if you have more than t minus 1 set, then you have t sets, because a t sunflower in this case is the same as just having t different sets. So case k equals 1 is obvious. And now let's do k minus 1. Transition k minus 1 to k, and how do we do it? So let's find the largest, find not even necessarily the largest, but a maximal matching in F. So a matching is just a collection of pairwise disjoint sets. So this would be A1, A2, etc. Well, M. So these are just pairwise disjoint sets from the family F, and the matching is maximal, meaning that we cannot add any more sets from F, so that it would be disjoint with all of those. So any set from F intersects one of these A1, etc., AM. So then, of course, each AI has size at most K by assumption. And also I claim that M is at most T minus 1. So why M is at most T minus 1? Because if M is at least T, then, well, these sets, they form a sunflower. So this thing is a sunflower just with empty core. So looking at this picture, just this thing being empty, or this thing being empty. So since we do not have, well, let's say, either it is a T sunflower immediately and we're done with the proof, or M is at most T minus 1. And if M is at most T minus 1, then we conclude that the union, the cardinality of union of AI is at most K times T minus 1, because, well, we just multiply these two bounds. And from here, we conclude that there is an element X belonging to this union such that f of x, let me write it here, such that f of x, meaning all sets from the family F containing x, well, let me leave it this way. The f of x is large. It has size at least the size of f divided by this k times t minus 1. So why is this? We said that the matching is maximal. So every set from F intersects the union of AI. So now let's just take the most popular element in this intersection, so the element that appears in most sets. Since in total we have at most that many elements, k times t minus 1, then one of them contains a k times t minus 1 fraction, k times t minus 1 fraction of all sets from F, and we take this to be x. So this is just what I wrote here. And this thing is bigger than, by the assumption of the size of f, bigger than k minus 1 factorial times t minus 1 to the power k minus 1. We just substituted the bound on f. From here, so now let's think about this f of x. What is this f of x? It's the family of all sets containing x. So removing x, all sets in this family have cardinality at most k minus 1. So we can apply induction to this family because the size is good. If you look at the statement, is exactly what we wanted for the case k minus 1, what we need for the case k minus 1, and we can apply induction. So from here, we conclude that f of x contains a t sunflower, but then we add x back to all sets, and we conclude that it now belongs to all sets in this sunflower and just contributes one element to the center, to the core. And from here, we get that f contains a t sunflower. So this is the proof. Okay, it's a simple and nice inductive proof. Okay, so now we'll discuss the recent improvements to this bound coming from Alvise and others. So let me introduce a general notation, which is similar to what I used above. So f of x, now x can be a set, is we take all the sets from the family f that contain this x and then remove it. Just the same way as we did before with one element. And the key definition for the talk would be this R spread definition. So this is very important. We say that the family f is R spread if this f of x decreases exponentially with the growth of x as compared to the whole family. So for example, if r equals to 2, then we want to say that at most 1/2 of the sets contain any given singleton, any given element. At most 1/2 proportion of the sets contain, at most 50% of the sets contain a given element. At most 25%, 1/4 contains any given 2 elements. At most 1/8 contain any given 3 elements, and so on and so on. So it is spread in the sense that there is no particular group of elements on which the family is unexpectedly dense. So too many sets from the family contain them. And you can think of this notion as some kind of quasi-randomness notion. And somehow we will derive very nice properties from it. Okay, so this is one notion that is very important. Another notion that is very important is, well, okay, but this is like, there is nothing specific about it, but we will often work with it. It's just a p-random subset of the ground set. So imagine that we live in a set X, and we say that W is a p-random subset of X if each element is included in X with probability P. So we will somehow relate this spreadness with the fact that sets from F would appear in p-random subsets of the ground set. So here is the exact statement. So I said roughly what this says just now, very roughly and very briefly. So let's look at it for 2 minutes maybe. This is very important. So we start with a family of sets of size at most k. in some ground set, again, n is superficial here, we do not really care. That is R spread. And if this family is R spread, and then somehow the parameters are chosen right, we haven't looked yet at the parameters, let's say what we conclude is that for M delta random, so subset W of n, so we somehow choose some parameter, the M and delta, so that this, we can think of this as 1/2 for the time being. So for example, for a random subset W of the ground set, so each element chosen with probability, say 1/2, the probability that we will have a set from our family lying entirely in this random subset, this probability would be large. So again, if parameters are chosen right, then this would be large. So with high probability, we see sets from our family in random subsets of the ground set. So this is what the statement says. Well, more precisely, we can look at the parameters. Typically, this thing inside is chosen to be such that this is 1/2 actually. 5 divided by this log is 1/2. And what is important is that M appears here as in the exponent, while here is just multiplies delta. So somehow this probability very quickly becomes 1, even for relatively small m. So if this thing is 1/2, it's enough to take m of order log k to make this term very small, and then somehow it triggers some dependencies. But the point is that from moderately small assumption on spreadness, you can derive this quite strong property. So one example here, one concrete example is that, let's say that R delta is 2 to the 10, then the probability behaves like this. So as I said, this would be just 1/2 inside. So it'll be 1 minus 2 to the minus m times k. And if we take then m to be 2 log k, then the probability becomes 1 minus 1 over k. So assuming k is large, this is small. And then we take delta to be p over m of some p. This way, this would be a p random subset. And yeah, so then we get that the p random W contains a set from the family with high probability. And the only thing we really need is, in this case, R to be sufficiently large. So R times delta, so R times P divided by M, or P divided by log K, to be 2 to the 10. So you can see that R is on order P log K, which is not actually such a strong assumption. We'll see in a second. Okay, so
me, Andre.
Yeah.
Is that a 5? 1 minus?
Here it's 5.
5. So just absolute constant.
Yeah. Just
okay.
And I stated this way so that actually you see that you can get actually not such big constants from this whole statement. Yeah.
Thank you.
So let's see a consequence, a concrete corollary. So if the family is R spread, for R behaving like this, it's 2 to the 11 T log Tk, then the family contains a T sunflower. So moderately, I mean, this is really not such a big spreadness. If you think about a 3 sunflower, which is already the bounds for 3 sunflowers were not much better than what Erdős-Rada result gave, and were of the order k to the power k. So here, if you think about t being 3, then R needs to be just some constant, not so big constant times log k. and then we can guarantee that F contains 3 sunflowers. So how do we get this? So the first thing is that we look at this theorem, and in the same way I just explained you, we conclude that 1/t random W contains a set from F with probability bigger than 1 minus 1/t. This is what you would get if you just substitute this R and choose the other parameters in the same way as I explained above. But then, okay, so what is the extra step? Then you use just union bound actually. So you randomly color the ground set in T colors. So each color, by randomly in T colors, I of course mean just
by randomly. Just a second. Can you hear me?
Чуть хуже, чем раньше, наверное.
У меня что-то наушники и ко всему прочему умерли. Сейчас буквально, простите, секундочку.
Вот это косуха, а?
Ладно, сейчас, да, я продолжу так, ничего страшного. Нормально слышно все-таки? Или плоховато?
Ну так, было лучше, но в принципе слышно.
Угу. Я сейчас поставлю наушники на зарядку и через минуту продолжу, простите.
Ну тогда пока так можешь.
Вот беспроводные технологии.
A small pause. Размять ноги пока. Чуток.
Так, а сейчас как слышно? Нормально?
Отлично.
Okay, I just took some other set of headphones. Can I have? So, okay. So what do? We color randomly the ground set into T colors. So each color assigned with probability 1/t. So each color in this way is just a 1/t random set, right? So for any given color, the probability that it contains a set from your family F is strictly bigger than 1 minus 1/t by this property. So this is what we have. And then we just do union bound over our T colors. So we have the star, if we call this thing a star, for each. Then do union bound over T colors. And this means that, well, for the first color, the probability is strictly bigger than 1 minus 1/t. For the second, it's strictly bigger than 1 minus 1/t to contain and set in the second color. And for the third, etc. So doing a union bound, we see that with probability strictly bigger than 0, there would be a set in each of these T colors. So if we had 10 colors, then it would be a set of color 1, color 2, etc., color 10. But these sets are obviously disjoint because they are of different colors. So these sets form a matching of size T, and thus they form a sunflower of size T. So they form a matching or a sunflower. Thus a sunflower, not or, thus. Well, they meaning the sets that we would have inside each color. I hope this is clear. If it's not clear, then ask questions. Good, thanks, Chair. Okay, so, but this is from the spreadness. How can we pass from spreadness to size? Well, this is actually not very difficult either. So what do we do? So the claim is as follows. If the family has this condition on size, so you can see it's just the previous R that we used here to the power K. Just this R to the power K. Then it contains a T sunflower. And if we compare with the previous result, before we had something like K to the K, and now we have log K to the K, and the conjecture is should be constant to the K. So this is this was a big step towards the Erdeschade sunflower conjecture. So how do we do it? This is very easy. Also, just find maximal A such that f of A violates the R spreadness condition with that R. So if we denote this thing by R, such that f of A a size bigger than R to the minus cardinality of A size of F. So we find the largest, the maximal A that violates the R spreadness condition. This A cannot have size K, for example, because then f of A would have size 1, and the size of A is chosen in such a way that this product would be bigger than 1. So it's somewhere between, well, 0 and the K strictly, smaller than K. Then the claim is that then f of A is R spread. Because if it's not R spread, we find the set violating the R spreadness condition. Say, if not, A prime violates, let's say A prime violates it, then f of A union A prime violates this, and thus A is not maximal. So this is essentially the argument. I'm not writing it with all details, but if f of A is not R spread, then there is a set disjoint from A called A prime that would also be large, and then together with A they would violate this inequality, contradicting the maximality of A. So we get that f of A is R spread, and then we just apply corollary to f of A. Corollary 1, let's say, if we call this corollary 2 and this corollary 1, we find the sunflower in f of A, we find the matching in f of A, find matching. T matching in f of A, it's a sunflower, a T sunflower in F. So that's the proof. These objects, this kind of objects are called robust sunflowers. So this kind of things. When we have a property like that, then we call it a robust sunflower because normal sunflowers are deduced. And so our spreadness implies having this robustness. Okay, but this was a big detour towards the result of Alwise, Lovett, Wu, and Zhang. But in the remaining maybe 10 or so minutes, I wanted to say about my results. I guess I'll try to be quite quick. So how can we use it for intersecting families, and what can we derive for intersecting? So we say that the family is intersecting if any two sets in a family intersect. So there is some classical result of Erdős-Cohen and Rado about how big an intersecting family can be. It's essentially if we fix the uniformity k, so all sets have size k, then the best we can do is fix one element and take all sets containing that. Then there are many questions you can ask about this. Intersection families, for example, you can prove different stability results, and meaning, okay, if the family is large, is it similar to the Erdős-Corrado example containing one element? And there are some degree versions. There are many different generalizations. It's a big topic, and the three main avenues for this type of questions. Okay, so extremal questions, for extremal set theory questions in general, but in particular for intersection families. So some of them are specific for intersecting families, such as shifting or using Kruskal-Kettner theorem. The two more general methods that exist, it's called the sunflower delta system method, which allows to detect certain structure in the family if it is large in one way using sunflowers. The other method is using Junta approximations. It's coming from Boolean analysis. And we complement these methods with a new method, which is called spread approximations. So maybe I'll skip the Junta method, but the point of this method, I give one exemplar result called the theorem of Dinur and Friedgut, which is for intersecting families. So the point is that if you start with an intersecting family, then there is a simple object, much simpler object called the J Junta, which would be also intersecting and which would approximate your family well. So most of your family would be contained in this Junta. And okay, 2 words about what is a Junta. So we say that a family is a J Junta. It's just a family of sets, but not a general family of sets. It depends on this J. Namely, there is a set of J coordinates, or if you think about it in 0, 1 terms, or if you think about it in set theory terms, just there is a set of size J at most, such that whether you are in the family or not only depends on the intersection with this J coordinates, set of J coordinates. So for example, if you think about this Erdős-Corrado example, then there, whether you are in the family or not, only depends on whether you contain or not that one element. So for example, element X. So all sets containing X. So if you contain this element X, then you're in the family. If you don't contain it, you're not in the family. So it's a one junta or a dictatorship in that case. Maybe your family is something like, okay, we want to contain at least 2 elements from the first 3. And then it would be a 3 junta. And this is the idea behind the junta. So somehow a function or a family, Boolean function or a family that depends on few coordinates or on a set of small size. And all the other elements are superficial. We don't care. We look only on the intersection. And the way you use this kind of approaches, so this junta approach, for example, is as follows. You approximate, you start with an extremal problem, you approximate your extremal family with some simple object, and for example, an L junta, with the same properties. If you were intersecting them, you are intersecting, or maybe even stronger properties. then you solve the problem for these juntas or for the simpler objects. It's simpler to solve for them because they have simpler structure. They depend on few coordinates somehow. In case of juntas, in case of sunflowers, also they possess some nice properties. Somehow it's easier to solve the extremal question in this class. And then what you conclude is that if your family was extremal, then you're approximated by an extremal junta. And the last step is somehow some local optimization. So you just show that your extremal family not only is close to your extremal junta, but it coincides with it. So changing it a little bit doesn't do anything. So, okay, so let me show you the one result. This is a theorem I proved before Dima joined this project. And it gives another approach for approximating intersecting families as follows. So you start with an intersecting family, and then you find an intersecting family now, which is not a junta, but just a family of sets of small size. Size at most Q, and Q is much smaller than K. And a remainder family of prime, such that you will have three properties which are very similar to what we saw before. The properties are as follows. Property one is that most of your family is somehow covered by S. So if you take a set from F minus F prime, then for this set, you will find a set from your family S, which would be contained in it. So somehow your family S captures all sets from here. Moreover, of course, S is intersecting, so this is very important. Then maybe second condition we can skip, but it somehow says that this family S is somehow quasi-random in some way. So for the applications, let's say it's not important. It's important some other things. And the third property is that the remainder is small. And what is important here is that, so this is the size of the sets that we get in the approximation. And this size goes in the exponent here in the estimating the remainder. So of course, the bigger you take this Q, the better you would get this approximation. But the point is that since it goes in the exponent already for logarithmic Q that is like logarithm of K, you get very meaningful results. Well, one maybe okay, so maybe Ljoš, do I understand correctly that I have basically no time, maybe a couple minutes, right? 2-3 minutes.
Что?
Лёш, правильно я понимаю, что у меня там буквально несколько минут или нет?
Сейчас
Да?
скажу. В принципе, еще 10, но если вопросы могут быть, то есть
Ага,
так
ну
по идее, и вопросы.
Okay, so maybe I'll spend 5 minutes. So the most impressive results, in my opinion, here are even not about intersecting families, but about some other objects, and I'll spend some time on these objects, I think. So here, for the intersecting families, is just an example of this thing. And the key point here, as I said, that it's a different type of approximation, not like juntas, but just, let's say, instead of juntas, low-dimensional polynomials, Boolean term. But the dependency is much, much better. In the previous result, I would not show it, but dependency between this kind of complexity of your family that you had and the size of the remainder was much worse. And it allows to prove some statements, like here there is one statement for showing that if you look at regular intersecting families, so families in which you have this property, so all elements have the same degree, and for regular intersecting families, you can show that they're extremely small. that that they're extremely small if n is somewhat large, bigger than k log k. So this, in general, this statement allows to prove many nice results in this regime, just bigger than k log k, essentially, which is not typical for other methods. Sunflower methods would give you some maybe exponential function of k or at least one, and Junta is bad enough. But maybe what so we have some new results for the what is called Erdős-Sors problem, where we forbid one intersection, which is like t minus 1, not only 0, t minus 1. But the main thing that I probably want, the thing I wanted to highlight is about permutations. So a nice thing about this method is that again, unlike say Junta method, is that it allows to focus on very small families that do not necessarily have some algebraic structure, but rather have this spreadness structure. And in particular, it allows to prove some very strong results about permutations. So well, we can look instead of families of sets, let's look at families of permutations. We say that this family of permutations is intersecting if for any two permutations, basically there is an element that they map to the same element. So if you take sigma and pi, then sigma of x is equal to pi of x. So actually you can transfer all properties families to permutations using the following logic, and in a very natural way. Maybe thinking about it in this way is a little bit complicated, but you can do the following. So you start from a permutation, for example, this one. You do a matrix, a permutation matrix. So here you see 1 went to 3, and this is why in row 1 we have 1 on the third column. So 2 went to 1, and now we write 1 in row 2, column 1, and same for the third one. So we do a permutation matrix. Then we make it a vector, just write rows consecutively, and we make it a set, just replacing 0, 1 vector by the set. So you can pass from permutation to a set here in n squared choose n using this identification. And then when we say intersecting permutations, is the same as saying intersecting sets here, or if you want, you can think about intersecting matrices. And then the same as for t intersecting, so intersecting in at least t elements or in exactly t elements, all these things. So, and then there is a big question for this permutation coming posed in the early 80s or late 70s by Desai and Frankel. What is the largest t intersecting family of permutations? For t equals 1, somehow it's even easier than Erdős-Corredo to determine that it's n minus 1 factorial. So all permutations fixing the first element. But even proving uniqueness of this configuration took a lot of effort, and there were 2 separate papers proving this uniqueness. And then to get this result for even t equals 2, like to determine the extreme for t equals 2 or any other constant t was a very, very, very serious kind of challenge. And people used complicated tools, and in long papers, so Ellis, Friedgut, and Pilpel solved this problem for every constant t, well, provided n is larger compared to this t. But they had to use representation theory together with, well, kind of non-commutative Fourier analysis and some additional combinatorics, probability, and so on. So it's like, it's long, like 40 pages paper, maybe 50 pages paper, with a lot of techniques involved and hard. So recently using a bit more modern version of these Juntas, but also with representation theory and some regularity types or probabilistic type things. Ellis and Lifshitz managed to also generalize it to the case of Erdős-Sors and get the results for Erdős-Sors. So we know the answer to this question and also to the question when we just forbid intersection t-1. But the point is that all of these papers are hard and don't give any explicit dependence between T and M. And with Dima Zakharov, using this combinatorial approach with no representation theory and much shorter proofs, we can get these results. And for T that grows polynomially with N. So we can show that if P, the family of permutation, is T intersecting, and T is smaller than roughly square root of N, then P has size at most n minus T factorial. So it means that the best we can do is fix T coordinates, like map 1 to 1, 2 to 2, T to T, and the rest is anything. Similar result for the for this condition. So when we say that no two permutation intersect in exactly T minus 1 elements, but now for T smaller than cubic root of N, roughly, again, same result. The best we can do is fix first T coordinates. So yeah, I think I'll stop here with this result. So thank you.
Thank you very much, Andrei. We have 2 minutes for questions. Joel, do you have questions?
I just say that this was one of Erdős's favorite problems, and this is a wonderful talk to see the progress. And it was a problem I worked on myself. The original sunflower, I got some very weak results, at least certainly compared to what we have today. So it's very exciting to see the new methods being used on these problems.
Yeah. Thank you.
Great. What about audience? The audience. Fyodor. Please wait for a.
Sorry.
Pardon.
Andrei, is count for T in the theorem really important? So without this restriction, does it hold? We don't know.
Can you say it again?
Say in this theorem, you need some bound for T, right?
Yeah.
What happens if it doesn't hold?
So actually, it's like Alsveda-Khachaturian's theorem, where you need some dependence between nk and t. But here, it should be that t is probably like smaller than n half. So this should be enough probably for these statements to hold. At least we don't know better construction. I'm not sure n half, but some constant like maybe n half or n over 3. So it doesn't hold for all t, but it holds to pretty large values of t.
But the proof doesn't work, right?
The proof doesn't work. Yes. It's it is important for our statement somehow, and yeah, we don't know how to get rid of this square root. Well, before I just again compared to previous results, this is much stronger because before it was just n was some function of t, so t was maybe smaller than log n before, or at least log n, at most log n definitely. So if you try to from here you try to get explicit dependency, it's definitely not better than log n. So in that sense, it's a progress, but there is room for improvement. We just don't know what to do.
And our last speaker for this day is my friend, Professor Joel Spencer from New York, whom we met first several years ago in Irkutsk, maybe 8 years ago, yeah?
Yes, a long time ago.
Long time ago, yes, and since that we met in Moscow and hopefully we'll meet again in the future when everything ends, you know. So, dear Joel, you have a floor. You are welcome.
Okay, so this will be a tutorial. These are wonderful games, the Ehrenfeucht games, sometimes called Ehrenfeucht Francais, but I knew Jan Ehrenfeucht, a wonderful man, so I like to call them Ehrenfeucht games. And so this meeting, we like to play games and analyze games, and these games connect in a very deep way to logic. So first, I begin with some quotations. One of my favorite quotations about Paul Erdős from Fan Chung, a wonderful mathematician at University of California, San Diego. She worked with Paul for many years. And I think for my Russian friends, you might like this wonderful quote from the great chess champion, Tao. You must take your opponent into a deep, dark forest where 2 + 2 = 5, and the path leading out is only wide enough for one. So I think that's good advice for life. Okay. All right, so here's the game. I first do it for graphs, but then I will show you it's much more general. There are two players, spoiler and duplicator. In the old literature, they're called player 1 and player 2. And my great contribution was I invented the words spoiler and duplicator for the players. There are two graphs, G1 and G2. And then there's a number of rounds of the game, K. This is a perfect information game. So you're given two graphs. They don't belong to either player. They're two graphs, G1, G2, and a number of rounds, K. And on each round, the first part of the round, the spoiler selects a point in either graph. And if it's the ith round, he labels that point I. And then duplicator must select a duplicate point in the other graph, Now, what do we mean by duplicate point? The main thing is that suppose that in one of the graphs, the third point and the fifth point are adjacent, then in the other graph, so suppose the first 4 moves have been made, and now spoiler plays a 5th move and in the first graph, and the third move and the 5th move are adjacent, then duplicator must play the 5th move in the other graph, so that again, the 3rd move and the 5th move must be adjacent. Also a technical point, if 2 moves are the same point, then duplicator must also make the same point. But that only occurs if there's less than K points in the graph. Otherwise, duplicator can always duplicate. So the main thing is you must preserve adjacency. So this is a perfect information game. And so either spoiler wins or duplicator wins. And here is the connection to logic, that duplicator wins this game if and only if the two graphs have the same truth value on all first-order sentences of quantifier depth at most K. And then we write G1 and G2 are equivalents of K. Now, to see that this is an equivalence relation, there's this very cute argument that suppose you had G1, G2, and G3, and duplicator wins with G1, G2, and duplicator wins with G2, G3, then duplicator can win with G1, G3, because he just pretends that there's a G2. So if spoiler moves in G1, he makes a pretend move in G2, and then he responds in G3. And if spoiler moves in G3, he makes a pretend move in G2 and responds in G1. So this is an equivalence relationship. So here's an example of this. Let's take the statement that the radius is at most 2, and let's consider the 3-move game. And suppose that G1 does have radius at most 2, but G2 doesn't. Then I claim that spoiler wins the 3-move game. So how does he win? First, he picks this central point x1. So then duplicator has to pick some y1, but there are points that are more than 2 away from y1. So then spoiler goes to the second graph and picks the y2 that's far away from y1. Now duplicator has to pick an x2 in G1. Of course, he can't pick x1 itself, and he can't pick it adjacent because you have to preserve adjacencies and non-adjacencies. But so that means that x2 and x1 are exactly 2 away. And then spoiler picks the x3 in the middle. So x1 is adjacent to x3 is adjacent to x2, but y1 and y2 are more than 2 apart. So duplicator loses and spoiler wins. Notice it's very important that the strength of this game is that duplicator can move back and forth between picking in G1 and picking in G2. That's very important because if he only had to pick in G1, you would just look at subgraphs of size K, but this is much, much stronger. Now, what do I mean by first order? I mean statements that look like this example, where you have the Boolean quantifiers, and then you have quantification, but critically, the quantification is only over vertices. You're not allowed to say there exists a set S such that blah, blah, blah. You're only able to say there exists a vertex X such that for all vertices Y, either Y is X, Y is adjacent to X, or there exists a Z that's adjacent to both of them. And what is quantifier depth? Well, you have these quantifiers, but they're nested. They're nested. So it's not the number of quantifiers, it's how deeply they are nested. Okay, I won't give a formal definition of that. I hope it's clear. So this is the critical theorem. Now here's a result that the number of classes is actually finite. This is not so immediate. The way we do this is to work backwards from the end of the game. Look at the number of possible positions where there are T moves remaining. And let's say graphs that have less than K vertices. So that's just a finite number anyway. So it's only adjacency we want to care about. So when there's 0 moves to go, there are only 2 to the K choose 2 possible positions. Now, if there are T plus 1 moves remaining, a position is where spoiler can go with 1 additional move. So he can go to one of the F of K2 positions. And so the position with T plus 1 moves to go is the subset of possible positions that spoiler can move to. And so what you get is that F of K T plus 1 is less than or equal to 2 to the F of K2. So to me, this shows that something deep is going on, because when you get down to T, you start at T equals K. When you get to, there's a typo here. The penultimate line should be F of KK, that is at the start of the game, and you get a tower of 2s, basically the tower function. And in fact, you can show that that's the right order of magnitude. It's not exponential. It looks like a tower function. So the number of positions up to equivalence is finite, But to show the depth of this game, it's actually a tower function of k, which means if k equals 10, we can't really play the game, well, unless you're Zhukovsky, who knows how to play it, but otherwise it's tough. Okay. Let me mention that there are lots of other structures here that you could look at. I'm going to say a little bit about rooted trees. There you have to preserve the root, and equality you always have to preserve, but it's never a problem. In fact, the root is not a problem. I mean, if one player plays on the root, the other, and the only thing you need to preserve is the parent relation. Or you can play it on partial orders where you have the less than relation and you have to preserve that. You can have what I call rooted trees plus, where you also have to preserve ancestor, critical. I'll make a comment at the end of the talk about that. And also you can look at monadic second order, and there you allow the spoiler to pick a set of elements and you have to preserve membership. So this is very, very general idea that Ehrenfeucht came up with. Now, what I like about this is that even if you don't know anything about logic, you can prove theorems in logic by playing games, or by analyzing games, I should say. So let's look at two graphs. G1 consists of an n cycle. We think of n as a Google. And G2 consists of two disjoint n cycles. Now, the claim is that if the number of rounds is fixed and n is sufficiently large, then duplicator can win this game. Well, I wrote exercise. It's not so easy to prove this. I mean, I'll show it in a moment, the idea behind it. But the point is that this is a purely combinatorial problem. In fact, and it's exactly the thing that we like. We like to analyze games. So we have to give a strategy for duplicator. Remember, K is fixed. So we're playing the 10-move game, and we, on one side, we have a cycle of size of Google, and on the other side, we have two cycles of size of Google, and we have to give a strategy for duplicator that will win. Okay, so I'm sorry, I moved. Let me back up here. Okay, but here is the implication for logicians that's very important, that connectivity is not expressible in first order. So non-expressibility is very important for logicians. You want to prove that you can't express a property in a particular language. And here we're talking about the first order language. Why is that? Suppose connectivity was expressible, so it would be expressible by a first order statement of length of quantifier depth K. And that would mean that if one graph had the property, was connected, and the other graph was not connected, then spoiler would win the K-move Ehrenfeucht game. But from the combinatorial exercise, we know that that's not the case, that duplicator will win. Sorry, that WITHS is supposed to be wins, will win. So, and this is very general. If you want to prove non-expressibility for a property A, all you have to do is show for every K, which is going to represent the quantifier depth, if for every K, you can find two graphs, one has the property and one doesn't have the property, and you can prove that duplicator wins, but that's what we're good at, analyzing games. That's what I'm saying. So then the deduction is that it's not expressible. So by playing games, we get powerful, powerful results. Now, here is a critical result. It's actually very, very general, but I'll look at it for graphs. It's called Geithman's locality theorem. Roughly that, let's fix the number of moves. So we want to know what class a graph is in. Basically, you just look at the local neighborhoods of size 3 to the k minus 1. Actually, that 3 to the k minus 1, there's an exact formula for it, but I'll just call it 3 to the k minus 1. So, but here, it's not quite that. So here it is. Again, I could make it even more precise. Suppose that G1 and G2 have the same balls. And when you look at a ball, I want to designate the center of that ball as, say, the first move of a K-move game. So a little technical stuff there. So suppose they both have the same balls. But furthermore, suppose that for every possible ball, and for both G1 and G2, if you take any K minus 1 vertices, you'll be able to find a ball that is far away from those K minus 1 vertices and is of that type. So that's an assumption. And then the conclusion is that duplicator can win the game. And here's the rough idea of the strategy. And this applies to the 2 big cycles. In fact, I think there you could use 2 to the t and it would work. But this is more general. What you do is when there are t moves to go, you make sure that if you look at the balls of radius 3 to the t around the points that have been played, so some of them may overlap, of course, but that's okay. So if you look at those, they're all equivalent. All right, so suppose we have that with t moves remaining. Well, if we have it with 0 moves remaining with the balls of radius 1, then that means we've won the game. So suppose with t moves remaining, they're there. And now spoiler makes a move. And there are 2 classes. Spoiler can move either inside or outside. And this is the Geithman idea. By inside, I mean within 2 times 3 to the t minus 1. So we're looking at balls of size 3 to the t. Inside is not near the boundary, within 2 times, just less than 2/3 of the way out to the boundary. If he plays inside, well, now after this move, we're only going to be looking at balls of size 3 to the t minus 1. So that's all going to be contained in this ball of size 3 to the t, so duplicator can make an equivalent play. On the other hand, if he plays outside, if he plays far away from the moves that have already been played, now his ball of radius 3 to the t minus 1 is an isolated ball. It's doesn't overlap with the other balls of size 3 to the t minus 1 of the previous points. So now, by the assumption of Geithman, duplicator can find a point far, far away that has the same ball. So this is the idea in somewhat an outline form, but this is the basic idea of Geithman's locality theorem. And because of that, that also gives for the cycles, okay. And so here's the application to 0-1 laws, that if you want to give a 0-1 law, which means that all first order statements have limiting probability 0-1, then you just have to show that if you take the 2 random graphs where m and n go to infinity, then with probability approaching 1, duplicator is going to win the k move. Again, for a given k, okay. And the proof is really quite quick, but let me just show one side. if the limiting probability was 0.3, then with probability 0.42 twice 0.3 times 0.7, G1 and G2 will differ on A, and so spoiler will win the K move. And the other side, we use the fact that there are only a finite number of possibilities up to quantifier K, quantifier depth K, and you just take the conjunction of all of them. And that occurs with limiting probability 0 or 1, and then that's enough. Okay. So here is one of my all-time favorite results given by in 1969 by Glebsky, Kogan. Sorry, my Russian pronunciation isn't very good. Lyagonki and Talinov in 1969. And then it was rediscovered by Ron Fagan in 1976. As you know from your ancient history, this was the dark days of the Cold War. And so communication between Russia and the United States was not so good. And the result is take any fixed P, then you have the 0-1 law. And the proof, given what we've already said, is immediate. The strategy for duplicator, well, he just never gets stuck. Suppose you've already played x1, x2, x3, and y1, y2, y3, and duplicator plays x4 that's adjacent to x1 and x2 and not x3. So, sorry, spoiler plays x4 adjacent to x1, x2, but not x3. So duplicator simply looks over and finds a y4 that's adjacent to y1, y2, and not y3. And so we need the simple result from random graphs that for n large, we can always do this. We can always do this. Okay. Let me give another example from Erdős-Rényi. If you look at P equals log n over n plus C over n, the number of isolated vertices is a Poisson distribution with mean e to the minus c. And so the probability that the graph is isolated, which turns out to be the probability that it's connected, is like e to the minus mu. So this was the classic Erdős-Rényi result about the threshold for connectivity. But in the first order world, we don't have connectivity, but we do have isolated points. So now if you look at the balls of radius 3 to the k, with a little bit of random graph results, you can show that you're going to get all trees. Now, what I mean by all trees, you only need to get a finite number of trees because you only need the equivalence class. And you get all the unicyclic possibilities, and you get nothing that's bicyclic or more. So this you need some random graph theory, but it's not particularly hard. And so what's left over is that the number of isolated points will determine your equivalence class with high probability. And if the number of isolated points is bigger than k, then it doesn't matter. So the only choices are 0 through k minus 1 and greater than or equal to k. If it's k or k plus 1, it's in the same class. And the conclusion then, what you get is you don't get a 0-1 law, but you get a complete description of the limiting probabilities. That they're all, basically all you can say is that the number of isolated, for k equals 10, is that the number of isolated points is 2 or 5 or greater than or equal to 10. Just statements like that. And so you get a complete description. And here's another example where you look at P equals C over N. It's interesting when, as many of you know, at C equals 1, you have the famous double jump, the phase transition, but you don't see the phase transition in the 0-1 law. So what you get is, if you look at the balls again, you get all trees in unicyclic and no bicyclic. No, sorry, all the balls are trees or unicyclic. And there are no, including isolated points, and there are no bicyclic. And every tree occurs many, many times. But the thing is, you may or may not have unicyclic graphs. So for example, the probability that you have no triangle is e to the minus mu, where mu is c cubed over 6. That was done in the original Erdős-Rényi paper, but now with the Janssen inequality, it's much simpler. Or you can say, what's the probability there's no isolated triangle? And that's e to the minus, that's a hyper-exponential function. And what you can show is that all the probabilities are given by iterates of polynomials and base e. Okay, just one moment here. Let me look a little bit at Galton-Watson trees. So these are our famous probability model. You start with a root, and each node has independently has Poisson lambda children. If you look going down from the root in this first order world with quantifier depth k, the root can have number of children up to k minus 1, but if it has more than k children, if you just look at depth 1, we count that as the same. And then if s equals 2, you could have like the root has 0 children with 0 children, 3 children with 1 child, you'll get 5 to the 5 types. And then you can talk about the property of the root as k gets bigger. And it turns out the probabilities, you get this iterated exponential type function. So let me just ask this for fun. I always enjoy this. So look at your mother's mother's mother, just to take an example. And let me ask you this question, true or false? She has no children that have no children that have no children. And it's a lot of fun. Let me say, I only speak 100 words of German, but it's actually very good in recursive German. So for those of you that do speak a little bit of German, seine Mutters Mutter, keine Kinder, die keine Kinder, die keine Kinder haben, hat, nicht wahr? Okay, well, it's fun to look at, and this connects to this. And it's interesting that when you write this with universal and existential quantifiers, they start to alternate. They alternate. Okay. Well, let me just blow my own horn here with my result with Shella, that using these methods, we were able to get a 0-1 law for n to the minus alpha, where alpha was an irrational number. And we could do it. We had several different proofs, but one proof gave a rather complicated duplicator strategy. You see, you have to be a little bit careful here. Suppose it's like n to the minus 0.6 and you're playing a 3-move game. And spoiler plays 2 points that are not adjacent. And suppose duplicator simply played 2 points that were not adjacent. But suppose spoiler was very clever and he knew that those 2 points had a common neighbor. And duplicator didn't notice that. So then spoiler would pick the common neighbor and duplicator would not. So what you have to have is a look ahead strategy, and it's a little bit complex. And so let me not give it, but that's good. Okay. Okay. Let me, let's see, 11:20. Maybe I can go 5 minutes over. Would that be okay? Because I got.
Yes, surely.
Okay, I just have some recent work by Mumanti Potter, who will be speaking tomorrow. but on different things. Let's look at Galton-Watson trees. And there are recursive properties. And a recursive property is you have a finite number of states for the trees. And the property and so the state of a node is the state of the tree going down from that node. And for the property to be recursive, the state of a node depends only on the states of its children. And then there's a further thing that there's a fixed number k so that you only count up to k. So if you have more than k red points, it doesn't matter how many more you have. So here's an example. Consider the property that every x has, at some point, has exactly one grandchild. This is recursive. You have to be a little clever. You can't do it with red and green. You have to do it with red, green, and yellow. And the way you do it is green is yes, yellow is no, but you have exactly one child. And red is everything else. So if you have a green child, then you're green. And all you have to have is greater than or equal to one green child, and then you're green. If you have exactly one child and that child is red, then you're yellow. If you have exactly one yellow child, if you have exactly one child and that child is yellow, then you're green, and otherwise you're red. Okay, so this is a fun thing. You can play around with properties and get this. Okay, and it turns out that properties are recursive except if and only if they're monadic second order, and which means quantification over sets, and that includes first order. So now if you have a recursive property, you can get equations, recursive equations for the probability. So here, let's call them x, y, and z. So if x, y, and z are the probabilities, the probability that you are yellow is you have to have exactly one child and it has to be red. So that's the first line, that's y. And then x, the probability that you're green, you could have exactly one child and it was yellow, that's x equals lambda e to the minus lambda y. Or, exclusive or, you can have at least one green child, and that's the 1 minus e to the minus x lambda. Okay, so, and z is, remember, these are distributions. So you only, now, if you, very nice calculus problem, this has a unique solution for any fixed lambda. Now, classically, if you look at the property that a tree is infinite, that's recursive too, because it's green or red, green if yes, red if no, and you're green if and only if you have a green child. So you get one equation and one unknown, because after all, it's distributions. If you have two colors, you only have one equation. But classically, I mean, I've taught this, and maybe many of you have taught this too. You get two, when lambda is bigger than one, you get two solutions to that equation. You get two solutions. And indeed, when Galton and Watson were doing this, this was very puzzling to them, that they got two solutions. And one of the solutions was that the probability of being infinite would be 0, and the other was some number bigger than 0. And so for a while, there was some confusion about that. But what I want to say is give Mumonti-Potter's result that not only do we have a unique solution in this particular case, but whenever we have a first order property, we get a unique solution. So let me okay, and let me not give the argument for that, but this was actually part of Mumonti's PhD thesis, and it was really a very beautiful result. So let me end with an open problem. And I'm going to express it in terms of cutoff. So I'm going to express it in a way where all we have to do is play games. Okay. So I want to look at what I called rooted plus. Sometimes it's called FOA, first order plus ancestor. And so in this game, the duplicator not only has to preserve parent, but it has to preserve ancestor. The difficulty here, I mean, this is a well-defined game on two trees. The difficulty is that you lose locality because everybody is the ancestor. You know, you can take an ancestor, which is the root, and then a descendant. So everybody you can reach via ancestor. And now here's the question that's an open question. I take a tree, well, except for probability 0. So almost surely you take a tree T, then there's going to be a finite cutoff. And the claim is that almost surely when you take this finite cutoff, that if you take, actually, if you take any two extensions of that finite cutoff, again, almost surely, then the duplicator will win the game. So that is, except for probability 0, the cutoff itself determines the value of the game. Let me express this in a slightly easier way. There's a finite cutoff, let's call it T1, such that for any extension of T1, except for probability 0, the duplicator will win the K-move game. Now here, let me notice that you can assume that the tree is infinite, because if the tree is finite and it only goes down 1,000 levels, you look at the cutoff at level 1,001, and now you know exactly what the tree is. So you can actually condition on the tree being infinite. And this is an open problem, so I like to end on an open problem that we've thought we had a solution many times, but we seem to be, this ancestor is quite tricky. But let me point out, it needs a little bit of probability because, why the probability? So suppose the tree was an infinite path starting at the root. Well, then wherever you cut it off, there would be a vertex of wherever you cut it off, all the vertices would have degree 1 or 0, but there'd be an extension where that vertex had degree 2, and so it wouldn't work. So you need this almost all part. Similarly, given almost all T1, if you cut it off at T, maybe from some vertex, some leaf, you might have an infinite path going down. So you need this almost all part. And this is an open problem that we're still struggling with. Let me end with a nice quotation by Herman Weil, and спасибо.
Спасибо огромное, дорогой Joel. Thank you very much.
You're very welcome.